Look up at the night sky on a clear, dark evening. What you see is a scattering of brilliant, distant stars, a serene and almost peaceful display. But that view is just the surface, a tranquil mask over a reality so strange and so deeply mysterious. It challenges the very limits of human understanding. What if I told you that the vast, beautiful cosmos we observe is filled with enigmas that even the brightest minds on Earth cannot crack? For every gleaming point of light, there is a shadowy question mark. For every galaxy spinning in the void, there is a phenomenon so baffling it defies our fundamental laws of physics. We have mapped the planets, sent probes to the edge of our solar system, and peered back in time to the dawn of the universe itself. And yet, the more we learn, the more we realize how much we truly do not know. This is not a story of what we have figured out. This is a journey into the great cosmic unknown, a tour of the most profound head-scratchers that keep astronomers and physicists awake at night. Imagine staring into the heart of a nebula like the pillars of creation, a place of breathtaking beauty where new stars are born. It seems like a place of creation and order, but hidden within that splendor are forces and occurrences that simply should not be. We are about to explore 25 of these cosmic riddles, from ghostly signals whispering across billions of light years to colossal structures in deep space that are so immense they challenge our entire conception of reality. This is not just a list of strange facts, it is an invitation to feel the awe and the humbling wonder that comes from confronting the absolute frontiers of knowledge. We are going to venture beyond the textbook answers and into the realm of the truly unexplained, where dark energy pushes the universe apart faster and faster, where galaxies exist without the dark matter we thought was essential, and where stars behave in ways that no model can predict. Each phenomenon is a piece of a puzzle we are only just beginning to assemble, a clue to a deeper truth about the cosmos and our place within it. So get ready to have everything you think you know about the universe challenged. This journey promises to expand your mind and ignite your sense of wonder, revealing a cosmos that is far stranger, far more beautiful, and infinitely more mysterious than we ever dreamed. Our journey into the unknown begins not with something exotic and invisible, but with the very stuff we're made of. You, me, the planets, the stars, all of it is composed of ordinary matter, what scientists call baryonic matter. It's the atoms and molecules that form everything we can see and touch. And yet, here is the first great cosmic shock. A staggering amount of this normal matter is missing. When cosmologists add up all the matter, they can directly observe every galaxy, every nebula, every speck of cosmic dust. The numbers fall desperately short. Based on our most precise measurements of the early universe, specifically from the afterglow of the Big Bang known as the cosmic microwave background, we know with great certainty how much of this ordinary matter should have been created. But when we look around at the universe today, roughly half of it is simply gone. It's a case of a cosmic inventory that doesn't balance, a profound oversight in our accounting of the fundamental building blocks of reality. This isn't about the mysterious dark matter or dark energy. This is about the material we thought we understood. So where did it all go? The leading hypothesis points to the vast, empty expanses between galaxies. Theorized in complex computer simulations of the cosmic web, this missing matter is predicted to exist as incredibly diffuse, hot filaments of gas strewn throughout the intergalactic medium. Think of the universe's structure as a sponge, where the galaxies are the dense knots and the missing matter is the faint, wispy web connecting them all. This gas is so hot and so thin that it doesn't emit light we can easily detect. It's essentially invisible to most of our telescopes. Finding it has required immense ingenuity. Astronomers have turned to distant, brilliant objects known as quasars, using them as cosmic flashlights. By analyzing the light from these quasars as it travels through billions of light years of space, they can detect the subtle absorption signatures of this warm, hot intergalactic medium, like seeing the silhouette of a faint fog against a distant lighthouse beam. These painstaking observations have started to close the gap, finding traces of the hidden matter exactly where the simulations suggested it should be. Solving this puzzle is absolutely vital because until we can fully account for the ordinary matter, our most fundamental model of the universe's composition and evolution remains fundamentally incomplete. If the missing ordinary matter is a cosmic accounting error, then the next phenomenon is the discovery of a ghost in the cosmic machine, an invisible hand that guides the fate of everything we see. We now encounter the single most dominant material in the universe, a substance so pervasive that it outweighs all the stars, planets, and galaxies 5 times over: dark matter. This is not a placeholder for something we simply haven't found yet, like the hidden gas filaments. We know dark matter is there with absolute certainty because of the powerful, unmistakable grip of its gravity. Picture a galaxy like our own Milky Way, a majestic pinwheel of billions of stars all orbiting a central core. According to the laws of gravity laid down by Newton and refined by Einstein, stars on the outer edges of this pinwheel, far from the central mass, should move much more slowly than those near the center, just as Pluto orbits the Sun far more sluggishly than Mercury. But when astronomers like Vera Rubin measured the rotational speeds of these distant stars, they found something astonishing. The outer stars were whipping around just as fast as the inner ones. The entire galaxy was rotating as if it were a solid disk, a motion that defied all gravitational logic based on the visible matter alone. The only possible explanation was that the galaxy was immersed in a colossal, invisible sphere of matter, a dark matter halo whose immense gravitational pull was yanking on those outer stars, speeding them up. This gravitational signature is echoed across the cosmos in another breathtaking effect: gravitational lensing. Einstein's theory of general relativity tells us that mass bends the fabric of space-time and light travels along these curves. A massive object like a cluster of galaxies can act as a cosmic magnifying glass, warping and distorting the light from even more distant galaxies behind it. Astronomers can map this distortion, creating a picture of where the mass in the foreground cluster is located. Time and again, these maps reveal vast amounts of mass where there is almost no light, a clear and elegant proof that an unseen form of matter is draped across the universe, sculpting its very structure. So what could this mysterious substance be? The hunt for its identity is one of the most thrilling pursuits in modern science. The leading candidate for decades has been a class of particles known as WIMP, or weakly interacting massive particles. These are theoretical particles that are heavy and, as their name implies, interact with ordinary matter only through the weak nuclear force and gravity. They would be everywhere, streaming through you and me and the Earth as if we weren't even here, only very rarely bumping into an atomic nucleus. To catch such an elusive ghost, scientists have built extraordinarily sensitive detectors and placed them deep underground, in abandoned mines and beneath mountains, where they are shielded from the constant rain of cosmic rays that would overwhelm the signal. These experiments wait in profound silence, hoping to record the minuscule vibration, the telltale ping of a WIMP collision. But WIMP are not the only suspects. Another compelling candidate is the action, a particle that is incredibly light but produced in vast numbers. Think of the difference between trying to find a few bowling balls hidden in a room versus finding a trillion grains of sand. Both represent the same total mass, but they require completely different detection strategies. Action hunters use powerful magnetic fields to try and convert these ghostly particles into detectable photons. Meanwhile, particle colliders like the Large Hadron Collider are trying to create dark matter particles by smashing ordinary particles together at nearly the speed of light, hoping to see missing energy in the aftermath that would betray the creation of something invisible escaping the detector. And in space, telescopes are scanning the skies for indirect evidence, such as the unique gamma-ray light that could be emitted if two dark matter particles were to accidentally annihilate each other. The profound irony is that we are surrounded by this substance, that it is the fundamental scaffolding upon which galaxies are built, and yet we have no idea what it is. Its existence is the bedrock of our modern cosmological model, a necessary component to explain the universe as we see it, and yet its true nature remains utterly, tantalizingly beyond our grasp. It is the universe's dominant material, and it is a complete and total mystery. Just when we thought the puzzle of dark matter was profound enough, the universe presented us with something even more baffling, a force so alien and counterintuitive it seems to rewrite the rules of physics in real time. If dark matter is the hidden gravitational glue holding galaxies together, then dark energy is its cosmic opposite, a repulsive force, an anti-gravity that is relentlessly pushing the entire universe apart at an ever-increasing speed. This discovery was so shocking and so contrary to established belief that it earned the astronomers who made it the Nobel Prize in Physics. The story begins in the late 1990s with two independent teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees. They were engaged in a meticulous project observing a specific kind of stellar explosion known as a Type I, a supernova. These cosmic blasts are what scientists call standard candles. They all reach roughly the same peak brightness because they are triggered when a white dwarf star accretes just enough mass to cross a critical threshold and explode. Knowing their true, intrinsic brightness allows astronomers to calculate their distance from Earth with remarkable precision. Furthermore, by measuring the redshift of their light, how much it has been stretched as the universe expands, we can determine how fast the universe was expanding when that light was emitted billions of years ago. The researchers were fully expecting to confirm that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down over time due to the collective gravitational pull of all the matter within it. It was a fundamental assumption, the cosmic equivalent of throwing a ball into the air and watching it slow as gravity tugs it back toward the ground. What they found instead sent a tremor through the entire foundation of cosmology. The distant, ancient supernova were significantly fainter than their predicted brightness. This meant they were much farther away than anyone had calculated. The only possible explanation was that the expansion of the universe had not been slowing down at all. In fact, it had been speeding up for the last several billion years. Some mysterious, unseen energy was working against gravity, forcing galaxies to flee from one another at a pace that grows faster with every passing moment. The name given to this unknown driver was dark energy, and today we understand it to constitute about 68% of the entire energy budget of the cosmos, dwarfing even dark matter. So what could possibly be causing this accelerated expansion? The leading candidate, championed by none other than Albert Einstein himself long before the discovery, is the cosmological constant. Originally, Einstein introduced this term into his equations of general relativity as a fudge factor to force the universe into a static, unchanging state, a notion he later called his greatest blunder when Edwin Hubble demonstrated the universe was indeed expanding. But in the wake of the supernova discoveries, the cosmological constant was resurrected with a new meaning. It represents a property of empty space itself, a constant, low-level energy density inherent to the vacuum. As the universe expands, more space comes into existence, and with it, more of this repulsive energy. This creates a positive feedback loop. The expansion creates more dark energy, which pushes harder, causing faster expansion, which creates even more dark energy. It is a runaway process with profound implications for the far future of the cosmos. However, this elegant solution is plagued by what many physicists consider the most embarrassing and severe discrepancy in all of science, the cosmological constant problem. When quantum physicists attempt to calculate the theoretical energy density of the vacuum of space, they arrive at a number. This number, based on the potential energy of all the quantum fields that permeate the void, is staggeringly, incomprehensibly large. In fact, their prediction is off by a factor of 10 followed by 120 zeros. To say this is the worst theoretical prediction in the history of physics is a dramatic understatement. It is as if you calculated the weight of a feather and got an answer heavier than the entire observable universe. This colossal failure means one of two things. Either our understanding of the quantum vacuum is fundamentally wrong, or some miraculous, perfect cancellation mechanism is at work that we do not yet comprehend. Other theories have been proposed to sidestep this problem. One suggests that dark energy is not a constant but a dynamic field, nicknamed quintessence, which could change over time. Another, more radical idea posits that our theory of gravity itself, Einstein's general relativity, breaks down on the scale of the entire universe and needs modification. Yet, despite decades of searching, the simple cosmological constant model, with all its glaring flaws, still best matches the observational data. The nature of dark energy is not just an academic curiosity, it is the single most important factor determining the ultimate destiny of everything. If the acceleration continues unchecked, we face a heat death or big freeze, where the universe expands so rapidly that all galaxies beyond our local group disappear over the cosmic horizon, leaving our descendants in an isolated, dark, and cold cosmos, unable to ever see or interact with the rest of the universe again. Unlocking the secret of dark energy is therefore the key to forecasting the final chapter of reality itself. But the grand cosmic tug of war does not end with dark energy's push. At the very same time, our entire galactic neighborhood is being flung apart by that repulsive force. We are also being pulled irresistibly toward a specific point in the void. This is the mystery of the Great Attractor, a colossal gravitational anomaly located in the direction of the Centaurus constellation, roughly 250 million light-years away. For decades, astronomers have tracked the motion of our Milky Way and found we are not drifting aimlessly. We, along with our entire local group of galaxies and the vast Virgo supercluster we belong to, are all streaming toward this unseen focal point at a breathtaking speed of over 2 million kilometers per hour. The force required to command such a universal motion must be staggering, the product of a concentration of mass so immense it was difficult to even conceive of. And for a long time it remained a ghost, a direction, a pull, but not a visible object. The primary reason for this obscurity lies in its cosmic address, a region of the sky astronomers poetically call the zone of avoidance. This isn't a place of cosmic danger, but rather a line of sight problem created by our own galactic backyard. When we look toward the center of our own Milky Way galaxy, we are peering through the dense gas and dust-filled plain of the galactic disk. This thick fog of cosmic material effectively blocks out most of the visible light from the universe beyond, creating a swath of the sky that appears relatively empty and unexplored. It's like trying to see a distant city through a dense personal fog. The Great Attractor was lurking directly behind that fog. For years, this zone was a major blind spot in our maps of the large-scale universe, perfectly positioned to hide one of the cosmos's most significant gravitational behemoths. The quest to unveil this hidden monster required new eyes telescopes that could see in wavelengths of light able to pierce through the galactic dust. Missions like NASA's WISE telescope, which surveys the sky in infrared light, were perfectly suited for this task. Infrared radiation, with its longer wavelengths, can pass through dust clouds that would completely obscure visible light. When WISE and other observatories trained their instruments on the zone of avoidance, the veil was finally lifted. They revealed not a single, impossible megastructure, but an enormous, previously unknown supercluster of galaxies. This structure, now named the Norma supercluster, is one of the most massive concentrations of matter in our entire cosmic neighborhood, a dense knot in the cosmic web containing thousands of galaxies. Its discovery provided the first concrete answer to the source of the Great Attractor's pull. The sheer collective gravity of all those galaxies was certainly a major factor in our motion. And yet, the mystery may have only deepened. While the Norma supercluster is undeniably massive, many scientists now question if it is truly massive enough to account for the full intensity of the gravitational current we are caught in. The observed velocity of our galactic flow seems to demand even more mass, suggesting that the Norma supercluster itself might be just a single part of a much larger structure. This has led to the proposal of an even grander attractor, a structure of almost unimaginable scale known as the Shapley supercluster. Located over 600 million light-years away, Shapley is the single largest concentration of mass in our local universe, a gigantic tapestry of interconnected galaxy clusters whose combined gravity could very well be the dominant force behind our motion. Our journey, then, appears to be a multi-stage one. We are being pulled toward the Great Attractor, which itself is being pulled toward Shapley. This reveals a cosmos of hierarchies within hierarchies, where what we once thought was the ultimate destination is merely a waypoint on a far grander voyage through the flowing rivers of space-time. The Great Attractor stands as a powerful reminder that even as we map the cosmos, the most significant forces shaping our path may still be hidden from our immediate view, their full scope only hinted at by our own relentless motion. Moving from the immense, slow-motion pull of galactic currents, we now shift our focus to a fleeting, brilliant moment, a signal that arrived from the depths of space and then vanished without a trace, leaving behind one of the most tantalizing mysteries in the search for cosmic intelligence. On a quiet August evening in 1977, a radio telescope known as the Big Ear, located at Ohio State University, was performing its routine scan of the heavens. This was not a glamorous operation. The telescope was essentially a giant, stationary ground reflector, and as the Earth rotated, it scanned a narrow strip of sky, printing its data line by line on continuous computer printouts. The data itself was a string of alphanumeric characters representing signal intensity, mostly a sea of zeros and ones, the background hiss of the cosmos. But a few days later, a volunteer named Jerry Amon was poring over these printouts when his eye caught something that made him stop dead. On the page for August 15th, next to a sequence of readings from the constellation Sagittarius, was a vertical column of characters 6EQUJ5. The letters corresponded to signal intensities so far off the normal scale that Amon, in stunned disbelief, simply circled the sequence in red pen and wrote beside it a single, now legendary word: wow. That one word would come to define the signal forever, but what made it so extraordinary, it wasn't just its strength. The wow signal was a narrowband radio signal, meaning it was concentrated on one very specific frequency, around 1420 MHz. This is profoundly significant because that frequency sits in a protected band of the radio spectrum, a quiet zone where earthly transmissions are forbidden by international agreement. It is a band dominated by the faint emission of neutral hydrogen, the most common element in the universe. Decades earlier, scientists like Philip Morrison and Giuseppe Cocconi had theorized that this hydrogen line would be a logical, universal channel for an advanced civilization to use for interstellar broadcasting, a sort of cosmic watering hole where any technological species might naturally gather. The signal also exhibited the telltale sign of a celestial origin. It rose and fell in intensity over exactly 72 seconds, precisely the length of time the Big Ear's fixed receiver would be trained on a single point in the sky as the Earth turned. It was the perfect profile for a beacon from the stars. The immediate and most thrilling possibility was that we had finally heard from someone else. The signal seemed to scream artificial, Yet science demands verification. The very first rule for any candidate signal is that it must be repeatable. And so began a decades-long quest. Astronomers pointed radio telescopes, including the immense Very Large Array, back toward that same patch of sky in Sagittarius, scanning for months and then years. They listened for anything: another powerful burst, a repeating pattern, a structured message. They heard nothing. The silence was absolute. The wow signal was a one-hit wonder, a cosmic cry that was never uttered again. This profound failure to find a repeat is what pushes the mystery from thrilling to deeply perplexing. If it was an intentional beacon, why was it only switched on for 72 seconds? If it was an accidental leakage from an alien civilization, like our own television and radio broadcasts, why have we never detected another whisper like it? The lack of a repeat forces us to scrutinize every possible natural explanation. One of the most discussed natural candidates emerged in 2016 when an astronomer proposed the signal could have been a reflection. The idea was that the radio waves from a pair of passing comets, which had not been known about in 1977, could have been bouncing off their vast clouds of hydrogen gas, creating a temporary bright signal. It was an elegant hypothesis, but it ultimately fell apart under scrutiny. The comets in question were not actually in the right part of the sky at the time, and more critically, comets do not emit strong, narrowband radio waves at the hydrogen line frequency. Other explanations have been floated, such as a signal from a secret military satellite or a brief, exotic stellar event. Yet, each one fails to fully account for the signal's unique characteristics: its precise frequency, its perfect intensity curve, and its origin in that uniquely quiet part of the radio spectrum. Every proposed natural cause has, so far, left at least one piece of the puzzle unresolved, and so the wow signal endures. It sits in a strange limbo, the one and only signal in the long history of SETI, the search for extraterrestrial intelligence that cannot be easily dismissed as human-made interference or a known astrophysical event. It is a ghost in the ether, a single, brilliant data point that hints at a universe that might be teeming with voices, yet remains stubbornly silent. It serves as both an inspiration and a cautionary tale, a reminder of how momentous a genuine detection would be, and how profound the silence that follows can feel. It fuels the hope that one day another signal will arrive, not as a fleeting, unconfirmed mystery, but as a clear, repeating, and undeniable hello from the cosmos. If you thought the wow signal was a brief and puzzling event, then prepare for a phenomenon that makes it seem almost leisurely by comparison. We now enter the realm of the cosmic flash, an event so transient and so violently energetic it pushes the limits of what we thought was possible. These are fast radio bursts, or FRB. Imagine for a moment compressing the entire energy output of our sun over 80 days into a single, blinding burst of radio waves that lasts for less than the blink of an eye, just a few thousandths of a second. That is the staggering power of an FRB. These signals do not originate within our galaxy. They are intergalactic travelers, voyaging for millions or even billions of years across the cosmic void before being snatched from the sky for a fleeting instant by our most sensitive radio dishes. The first one was discovered only in 2007, hidden in archival data from the Parkes Radio Telescope in Australia, and for years many in the astronomy community were skeptical, wondering if these were just glitches or some form of local interference. But as more and more were found by different telescopes across the globe, the reality became undeniable. The universe is crackling with these intense, mysterious explosions. A major breakthrough in understanding this chaos came when astronomers realized they could separate these bursts into two distinct families. The vast majority appear to be one-off events, solitary explosions that detonate in a distant galaxy and are never heard from again. These non-repeating FRBs are like cosmic firecrackers popping off in the dark, but then there are the repeaters. The first confirmed repeater, known as FRB 1211-2, was a game-changer. After its initial blast was detected, astronomers pointed the massive Arecibo telescope back at its location and witnessed it erupt again and again, each burst a frantic, milliseconds-long shout from the same corner of the cosmos. This single observation ruled out any cataclysmic, self-destructing source for at least some of these events. You cannot have a repeating explosion if the source is obliterated in the initial blast. This crucial distinction meant that whatever engine was powering the repeaters had to be capable of surviving its own outburst, or be part of a system that could produce multiple flares over time. So what cosmic object could possibly be both incredibly destructive and durable enough to produce these flashes? The current leading suspect for at least some FRBs is a type of stellar corpse known as a magnetar. A magnetar is a neutron star, the incredibly dense, city-sized remnant of a massive star that went supernova, but with a truly monstrous magnetic field. To grasp the intensity, consider that a typical refrigerator magnet has a field of about 100 Gauss. The Earth's protective magnetic field measures less than 1 Gauss. A neutron star can reach 1 trillion Gauss. A magnetar, its field is 1,000 times stronger still, reaching 1 quadrillion Gauss. These fields are so powerful they literally stress the star's crust, causing starquakes that can release titanic flares of energy. It is theorized that an immense starquake on a magnetar could violently reorganize its magnetic field lines near the surface, launching a shock wave that, as it plows through the surrounding plasma, generates an intense, coherent blast of radio waves, a fast radio burst. In 2020, we caught one in the act. A magnetar within our own Milky Way galaxy erupted in a burst that, while not as powerful as the extragalactic FRBs, shared many of the same spectral characteristics, providing the first direct observational link between a known object and this mysterious phenomenon. But magnetars are likely not the whole story. The incredible diversity in the strength, repetition patterns, and even the polarization of the radio waves from different FRBs suggests we may be dealing with multiple cosmic culprits. For the non-repeating bursts, the cataclysmic merger of two ultra-dense objects, like neutron stars, remains a compelling explanation. As these stellar remnants spiral inward in a final, deadly dance, they could eject material and create magnetic conditions just right for a single, colossal radio blast. Some FRBs, however, exhibit properties so strange they have prompted scientists to explore even more exotic frontiers of physics. Could they be the result of cosmic strings, hypothetical, one-dimensional defects in the fabric of space-time left over from the Big Bang, snapping and releasing immense energy? Or what about the evaporation of primordial black holes, those theorized tiny black holes that may have formed in the universe's first moments? The sheer power and brevity of these signals have even led to a small but serious discussion about engineered origins. Could an advanced civilization be using incredibly powerful pulses to propel light sails across interstellar distances, with the radio burst being a side effect? Or are they beacons intended for communication? While this is considered the least likely explanation by most astronomers, the fact that it can be seriously proposed at all underscores just how baffling the complete picture remains. Each new detection, especially from powerful new facilities like the CHIME telescope in Canada, which is discovering them by the dozens, adds another crucial piece of data. By pinpointing the host galaxies of these bursts, astronomers can study the environments that give birth to them, whether they are in old or young galaxies, in regions of furious star formation or quiet stellar cemeteries. This contextual information is the key to unraveling the mystery. Fast radio bursts are more than just a cosmic curiosity. They are also powerful new tools for probing the universe. As these radio waves travel across billions of light years, they pass through diffuse clouds of ionized gas that are otherwise invisible. This gas subtly smears out the signal, and by measuring this smear, scientists can essentially weigh the missing ordinary matter we discussed earlier, providing an independent check on our cosmic inventory. So, in their fleeting brilliance, these enigmatic flashes are not just posing a profound question. They are also helping us answer others, illuminating the dark, vast spaces between galaxies in a way we never thought possible. And just when we thought we had seen every kind of stellar behavior, the universe presented us with a star so bizarre it single-handedly revived a fringe scientific idea and captivated the world. In the constellation Cygnus, 1,200 light-years away, lies a star officially named KIC 8462852, but now known to millions as Tabby's star, after the astronomer Tabitha Boyajian who led its initial study. To the naked eye, it's an utterly ordinary, moderately faint star, but its light curve, the graph of its brightness over time, is anything but normal. It was first flagged not by a professional astronomer, but by citizen scientists participating in the Planet Hunters project, sifting through the overwhelming torrent of data from NASA Kepler Space Telescope. Kepler's primary mission was to find planets by detecting the subtle, periodic dimming that occurs when an exoplanet transits or crosses in front of its host star. These dips are typically tiny, on the order of 1% or less, and they repeat with clockwork regularity. What the volunteers found in the data for this star was something completely different. They saw deep, jagged dips in brightness, some plunging by an astonishing 22%. This wasn't the clean, symmetrical shadow of a planet. It was a chaotic, unpredictable dimming, as if something massive and irregular were intermittently blocking the star's light. The pattern was unlike anything ever recorded. The sheer scale of the dimming immediately ruled out a planet. To block that much light, an object would need to be colossal, far larger than any known planet. This is where the story took its most sensational turn. In an era increasingly open to the possibility of life elsewhere, one of the first and most captivating hypotheses proposed was the idea of an alien megastructure. The physicist Freeman Dyson had once speculated that a sufficiently advanced civilization, needing to harness the entire energy output of its star, might construct a vast swarm of orbiting collectors, a Dyson sphere encasing the star and capturing its light. The bizarre, aperiodic dimming of Tabby's star seemed to fit this wild concept perfectly. Perhaps we weren't looking at a natural object, but the partially completed construction project of a Type 2 civilization, with immense panels or habitats drifting in front of the star in an irregular pattern. The idea, while extreme, was a legitimate, if last resort, scientific hypothesis. It wasn't a claim of discovery, but an acknowledgement that natural explanations had to be thoroughly investigated and ruled out before such an extraordinary conclusion could even be entertained. And so began a massive, multi-year observational campaign to do just that. The natural explanations proposed were as creative as the star's behavior was strange. One early and prominent theory involved a truly immense swarm of comets. The idea was that a vast family of icy bodies, perhaps disrupted by the gravitational influence of a passing star, could have been sent falling inward in a series of grand, dusty processions. As these comets approached the star, they would vaporize, creating enormous, opaque clouds of dust and gas that could account for the deep, irregular dimming. While this could explain the lack of a repeating pattern, the theory stretched credibility to its limit. The number of comets required would be staggering, numbering in the millions, all on wildly eccentric orbits, and their collective behavior would have to be coordinated in a way that is difficult to model. Furthermore, observations from the Spitzer Space Telescope, which views the universe in infrared light, failed to detect the excess heat that such a massive cloud of dust should be emitting. If there was dust, it seemed to be unusually cold. This led to other, even more intricate models centered on dust. Perhaps the star was surrounded by a vast, clumpy ring of debris, similar to the disk around the young star Fomalhaut, but on a far more chaotic scale. Within this disk, massive clumps of planetary building material or the shattered remains of a catastrophic collision between protoplanets could be orbiting, casting their deep, irregular shadows. Another compelling idea posits that the star itself is to blame. Some variable stars pulsate, but Tabby's star doesn't show the classic signature of a pulsator. However, it might be in a unique post-cataclysmic state. What if it had recently devoured a planet? The violent disruption of a gas giant wandering too close could have thrown an enormous amount of debris into a highly elliptical orbit, creating a long-lasting cloud of fragments that continue to transit for centuries. Or perhaps the star possesses a powerful, dynamic magnetic field that is driving immense star spots, far larger than any sunspot on our Sun, which could cause significant dimming as they rotate in and out of view. Each of these natural explanations has its merits and each its flaws. The comet swarm theory struggles with the required scale and the lack of infrared signature. A debris disk would need to be incredibly fine-tuned to produce such sharp, deep dips without being completely visible. A planetary disruption is a one-time, catastrophic event, yet the dimming has persisted for years, albeit with changing patterns. The truth is, Tabby's star has refused to be pigeonholed. Follow-up observations, including a wildly successful Kickstarter campaign that funded time on a global network of telescopes, have shown that the star dims not just in the deep, dramatic events, but also on a much longer, subtler timescale, fading by a few % over the course of the Kepler mission. This points to a multifaceted phenomenon with both fine, microscopic dust and larger, macroscopic chunks likely playing a role. While the thrilling speculation about a Dyson sphere has now been largely set aside by the scientific community, the observed properties of the dimming, particularly how it affects different colors of light, are consistent with ordinary starlight being blocked by dust, not solid panels. The ultimate solution is still out of reach. Tabby's star remains one of the most unique objects in the sky, a stellar maverick that defies easy classification. It has become a living astrophysical laboratory, forcing us to reconsider the full range of possible behaviors in middle-aged sun-like stars. It taught us the power of citizen science, the importance of methodically testing even the most exciting ideas, and above all, the humbling lesson that for all our knowledge, a single, unassuming star can still present a mystery that captivates the entire planet. From the tantalizing, isolated signal of wow to the frantic, brilliant flashes of FRBs, we've seen how the cosmos can tease us with possibilities. But what happens when we step back from these individual mysteries and consider the universe as a whole? We are immediately confronted by one of the most profound and unsettling questions ever asked, a puzzle known as the Fermi paradox. It all began with a casual lunchtime conversation in the summer of 1950. The brilliant physicist Enrico Fermi, while chatting with colleagues about flying saucers and the potential for interstellar travel, suddenly blurted out a question that was both simple and devastating. Where is everybody? He wasn't just being flippant, he was pointing to a staggering contradiction that has only deepened with time. Let's break down the logic. Our galaxy, the Milky Way, contains an estimated 100 to 400 billion stars. A significant fraction of those stars are likely to host planets, with many orbiting within the habitable zone where temperatures could allow for liquid water, a key ingredient for life as we know it. Our galaxy is also incredibly ancient, over 13 billion years old. That is an almost incomprehensible amount of time for life to arise, evolve, and for intelligent technological civilizations to emerge. Even if only a tiny, tiny fraction of stars ever gave rise to a spacefaring species, the numbers suggest the galaxy should be teeming with life. By conservative estimates, there should be thousands, perhaps even millions, of advanced civilizations. If just one of them had begun expanding across the galaxy a mere few million years ago, a blink of an eye on the cosmic scale, they could have easily colonized every suitable star system by now. Their presence should be unmistakable. We should see the glow of their engineering projects, hear the constant chatter of their communications, or find the artifacts of their exploration. And yet, when we gaze upward, we are met with an immense and powerful silence. The cosmos appears utterly, profoundly empty. This is the heart of the paradox, the crushing disparity between our high expectations for life and the complete absence of any observable evidence for it. This eerie silence has prompted scientists to propose a host of possible solutions, each more thought-provoking than the last. One of the most sobering ideas is the Great Filter hypothesis. This theory suggests that the evolution of life from its basic origins to a galaxy-spanning civilization is not a smooth, guaranteed process. Somewhere along that long and treacherous path, there exists a barrier, a filter, that is extremely difficult or perhaps even impossible to overcome. The terrifying implication is that this filter might still lie ahead of us. Perhaps the development of complex, multicellular life is the rare event. Or maybe the emergence of tool-using intelligence is the bottleneck. But the most chilling possibility is that the filter is something that awaits all technological species, perhaps a nearly inevitable self-destruction through nuclear war, engineered pandemics, or runaway artificial intelligence. In this scenario, the reason the galaxy is silent is that no one makes it through the technological adolescence that we are currently experiencing. The Great Filter stands as a cosmic caution sign, a possible explanation for the silence that serves as a stark warning for our own future. A much more benign, though equally strange, solution is the zoo hypothesis. This idea proposes that advanced extraterrestrial civilizations are indeed out there, and they are fully aware of our existence. However, they have deliberately chosen to conceal themselves, placing our planet in a kind of cosmic wildlife preserve or anthropological park. They observe us from a distance, refusing to make contact until we have reached a certain level of maturity, perhaps a point where we have overcome our own self-destructive tendencies and joined the galactic community as a peaceful species. It's a compelling thought, but it raises its own difficult questions. Why would every single civilization across the entire galaxy agree to such a strict, universal policy of non-interference? Could a directive like the Prime Directive from Star Trek really be adhered to by every species without a single rule breaker in billions of years? Then there are the more practical, physical explanations. The sheer, mind-numbing scale of space itself could be the ultimate insulator. The distances between stars are so vast that even traveling at a significant fraction of the speed of light, a journey to our nearest neighbor, Proxima Centauri, would take thousands of years. Communication faces the same hurdle. A simple hello sent to a civilization 1,000 light-years away would take a millennium to get there and another 1,000 years for a reply to return. It's possible that the universe is simply too big and too old for synchronous conversations to be practical. Civilizations may flare into existence, broadcast for a few centuries, and then fade away into silence long before their signals ever reach another listening ear. We could be like ships passing in the night, separated by an ocean of time as well as space. Other explanations push the boundaries of our imagination even further. Perhaps we are looking for the wrong things, searching for radio signals when truly advanced beings have moved on to technologies we can't even conceive of, like communication through quantum entanglement or manipulation of dark matter. Or maybe intelligence itself is not the evolutionary pinnacle we assume it to be. It's possible that consciousness and technology are a dead end, a maladaptive trait that inevitably leads to a species extinction, or simply a path that most life forms never evolved to pursue. Perhaps the universe is filled with the equivalent of dolphins and crows, intelligent beings who never feel the urge to build radio telescopes or rockets. The Fermi paradox forces us to confront the most fundamental questions about existence. It asks us not just to wonder if we are alone, but to question what life is, what intelligence is for, and what the ultimate fate of a conscious species might be. In the end, the Great Silence may be the most important message the universe has ever sent us. It is a mirror reflecting our own hopes, our fears, and the profound responsibility that comes with being the only talking creatures, so far as we know, on a pale blue dot suspended in a seemingly infinite and silent void. But sometimes the clues to the universe's deepest secrets aren't found in distant galaxies or brilliant stellar explosions, but in the subtle, almost imperceptible drift of a human-made machine on a quiet journey into the void. This brings us to the curious case of the Pioneer anomaly. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were true trailblazers, the first spacecraft to travel through the asteroid belt and the first to make close-up observations of the outer gas giants. After completing their primary missions, they continued on trajectories that would carry them out of the solar system entirely, becoming silent ambassadors from humanity drifting in the interstellar dark. For decades, scientists at NASA, a jet propulsion laboratory, meticulously tracked their positions using the Deep Space Network, a global system of radio antennas. They would send a precise signal to the spacecraft, which would then return a signal of its own. By measuring the subtle shift in the frequency of this returned signal, a phenomenon known as the Doppler effect, they could calculate the probe's velocity and position with astonishing accuracy, down to a few millimeters per second. It was during this long-term tracking that engineers began to notice something peculiar. Both spacecraft, now millions of miles from the sun and coasting freely, were experiencing a tiny, unexpected deceleration. It was an incredibly small force, about 10 billion times weaker than the gravity we feel pulling us to the Earth's surface, but it was persistent and unidirectional. It was as if an invisible hand were gently applying the brakes, a slight but constant tug pulling the Pioneers back toward the inner solar system. This minuscule drift was far too small to affect the missions operationally, but for physicists it was a potential bombshell. Any unexplained motion in a gravity-dominated system is a red flag, a possible hint that our understanding of gravity itself, as described by Einstein's general relativity, might be incomplete on the vast scales of the solar system. Could this be the first tangible evidence of a modification to Newton's law of gravity? Or perhaps it was a sign of unseen, non-luminous matter in the outer solar system exerting a gravitational pull. The anomaly captivated theorists and experimentalists for years, becoming a classic unsolved problem in physics. Solving this mystery required a Herculean effort in forensic space archaeology. The original engineers who built the probes were retired, and much of the design documentation was stored on archaic media formats. A dedicated team led by Slava Turyshev spent years recovering old data tapes, digitizing decades of telemetry, and even rebuilding the spacecraft's blueprints and thermal models from scratch in sophisticated computer simulations. They had to account for every conceivable force acting on the distant probes, the gravitational pull of every planet and known asteroid, the minuscule but cumulative pressure from the solar wind, even the tiny recoil from the craft's own radio signals being transmitted back to Earth. One by one, these potential culprits were investigated and ruled out. The anomaly remained. The painstaking work ultimately pointed to a much more mundane, yet fascinating explanation: heat. Not the heat from the sun, which was negligible at that distance, but the heat from the spacecraft themselves. The Pioneers were powered by radioactive thermoelectric generators, which produced both electricity and a significant amount of waste heat. The team's detailed thermal modeling revealed that this heat was not radiating away from the spacecraft perfectly evenly. A little more heat was being emitted from the back of the craft's main dish antenna, which faced toward Earth, than from the sides. This tiny anisotropy, this lopsided radiation of infrared photons, acted like a soft, continuous thruster, pushing gently against the direction of travel and creating the observed deceleration. It was a brilliant and elegant solution, a triumph of meticulous engineering analysis. However, as with many good cosmic mysteries, a sliver of uncertainty remains. While the thermal radiation explanation accounts for the vast majority of the anomalous acceleration, some analyses suggest there might be a tiny residual effect that it doesn't fully explain. This lingering sliver is so small it could still be an unaccounted for systematic error in the incredibly complex models, but its existence keeps a small window open for more exotic possibilities. Could there be a subtle, long-range effect in gravity that only becomes noticeable in the extremely weak field environment of the outer solar system? The Pioneer anomaly, in the end, stands as a powerful lesson in scientific humility. It showed us that our deepest theories can be challenged by the slightest of whispers from the data, and that the most profound answers often lie in patiently understanding the intricate details of our own creations. It was a decades-long reminder that to hear the universe's faintest signals, we must first learn to silence all the noise we make ourselves. Just when we thought we had our own solar system somewhat figured out, the universe sent us a visitor from a place we can only dream of, an object that defied every expectation and left a trail of questions in its wake. In October 2017, astronomers at the Pan-STARRS Observatory in Hawaii spotted a tiny, fast-moving point of light that didn't match the orbit of any known asteroid or comet. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And that's exactly what it was, the very first confirmed object from interstellar space ever detected passing through our cosmic neighborhood. The initial excitement was palpable. Here was a piece of another star system, a rare chance to directly examine material forged around a distant sun. But as more data came in from telescopes around the world, that excitement quickly turned to profound bewilderment. This was no ordinary space rock. Everything about Oumuamua was strange, starting with its shape. By carefully analyzing how its brightness changed over time, astronomers determined that it was tumbling through space, and the extreme variations in its light curves suggested an utterly bizarre geometry. It wasn't a roughly spherical lump like most asteroids. Instead, Oumuamua appeared to be highly elongated, shaped like a cigar or perhaps a pancake, with its length estimated to be up to 10 times greater than its width. This made it far more elongated than any known object in our solar system, a form that immediately raised questions about what kind of processes could create such a strange shape in the first place. But the biggest surprises were yet to come. As Oumuamua completed its slingshot around the sun and began its high-speed journey back out into interstellar space, astronomers tracking its trajectory noticed something that simply couldn't be explained by gravity alone. Its path was deviating slightly from the perfect elliptical orbit dictated by the sun's gravitational pull. It was speeding up. This kind of non-gravitational acceleration is something we see in comets all the time. As a comet approaches the sun, its icy surface heats up, causing ices to vaporize and erupt in jets of gas and dust. This outgassing acts like a natural rocket engine, giving the comet a small push that can alter its course. The crucial difference with Oumuamua was that it showed no visible signs of this activity. When we look at a comet, we see a coma, a fuzzy, glowing envelope of gas and dust, and often a tail that can stretch for millions of miles. Oumuamua had none of that. Despite some of the most sensitive telescopes in the world, including the Hubble Space Telescope, training their gaze upon it, the object remained a stark, point-like pinprick against the blackness of space. It was accelerating as if it were a comet, but it looked completely like an inert, rocky asteroid. This was the central, baffling contradiction that launched 1,000 theories. The scientific community scrambled for explanations that could fit these bizarre observations. One of the first and most developed natural hypotheses was that Oumuamua was in fact a comet, but an exotic one made of very different stuff. A team proposed it could be a hydrogen iceberg. The idea was that in the cold, dense cores of giant molecular clouds, large chunks of solid hydrogen could form. As this hydrogen iceberg neared the sun, the theory went, the solar radiation would cause the frozen hydrogen to sublimate directly from solid to gas, providing the thrust for the acceleration. Because hydrogen gas is invisible to our telescopes, this would explain the lack of a visible coma. However, this model faced a serious challenge. It's incredibly difficult for a large chunk of solid hydrogen to survive a journey of millions of years through interstellar space without being evaporated by the faint background radiation that permeates the galaxy. Another prominent theory suggested it was a nitrogen iceberg, a large chunk ripped from the surface of a Pluto-like exoplanet in a distant star system. Nitrogen ice is sturdy, and when it sublimates, it could provide the necessary push. This idea gained some traction, as we know vast glaciers of nitrogen exist on Pluto. But again, the theory required a very specific and massive fragment to be ejected, and the amount of nitrogen that would have needed to sublimate to produce the observed acceleration was immense, potentially requiring the object to have lost a significant fraction of its mass during its brief solar flyby. It was into this arena of competing, complex natural explanations that a truly extraordinary hypothesis was thrown. Harvard astronomer Avi Loeb proposed that Oumuamua's peculiarities could be explained if it were not a natural object at all, but a piece of advanced alien technology. Specifically, he suggested it could be a light sail, a vast, thin, reflective sheet designed to be pushed by the radiation pressure from starlight, much like a sailboat is pushed by the wind. This, he argued, would neatly account for the non-gravitational acceleration without the need for outgassing. The pressure from sunlight itself would be enough to give a large, thin, lightweight object like a sail a measurable push. The object's unusual shape would also be consistent with a designed sail, and its unusual brightness, it was unusually reflective for its size, could be explained by a smooth, metallic surface. Loeb's proposal was met with intense skepticism from much of the astronomical community, who argued that an extraordinary claim requires extraordinary evidence, and that we should exhaust all possible natural explanations before leaping to an interstellar artifact. The debate grew heated, playing out not just in scientific journals but across global media, turning Oumuamua into a household name and sparking a public conversation about how we approach the unknown and the limits of our scientific imagination. Ultimately, Oumuamua sped away from us far too quickly for a definitive close-up study. It is now beyond the orbit of Neptune, too faint to observe, and it will never return. Its true nature is destined to remain one of the great unsolved cosmic mysteries of our time. Was it a bizarrely shaped comet that vented invisible gas in a way we'd never seen before? Was it a fragment of a shredded planet, a new class of interstellar object we were lucky enough to glimpse? Or was it, as some still wonder, our first brush with a relic from another civilization, a silent, derelict ship adrift on the tides of the galaxy? Oumuamua serves as a powerful and humbling reminder that the universe is capable of producing phenomena that lie entirely outside our current catalogue of experience. It was a single data point, a messenger that passed through our backyard for a few short weeks, and in doing so, it challenged our assumptions and expanded our sense of what might be possible out there in the vast darkness between the stars. Leaving behind the interstellar enigma of Oumuamua, we now turn our gaze to a mystery much closer to home, a puzzle hiding in the deep freeze at the very edge of our own solar system. Far beyond the orbit of Neptune lies a vast, donut-shaped region known as the Kuiper Belt, a cosmic junkyard filled with frozen remnants from the solar system's birth. For decades, astronomers have theorized that this belt should be teeming with countless small, icy worlds, a gradually thinning population of objects stretching far out into the darkness. But when we finally developed the technology to take a proper census of this distant realm, we were met with a head-scratching discovery. Instead of a slow and steady fade into nothingness, the Kuiper Belt simply ends. It's as if you were walking through a forest that grows progressively denser, only to suddenly step off a cliff into an empty plain. This is the Kuiper Belt Cliff, a sudden and dramatic drop-off in the number of objects observed beyond a distance of about 50 astronomical units from the Sun, with 1 astronomical unit being the average distance from Earth to the Sun. This isn't just a minor statistical blip, it represents a fundamental challenge to our most established models of how planetary systems form. The leading theory, known as the NICE model, paints a picture of a violent and dynamic early solar system. In this scenario, the giant planets Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. They migrated, shifting their orbits and gravitationally scattering a vast sea of primordial icy planetesimals outward. This process should have created a rich, extended disk of debris, with the Kuiper Belt being just the inner, most densely packed edge of a much larger structure called the scattered disk. According to these simulations, we should be finding a significant number of small worlds orbiting far beyond the 50 mark. The fact that we don't suggests that something intervened, either clearing out that distant region or preventing it from being populated in the first place. It's a cosmic crime scene where the evidence doesn't match the expected story, and the prime suspect for many astronomers is a hidden, massive object whose gravitational influence has sculpted this strange boundary. This is where the tantalizing hypothesis of Planet 9 enters the stage. The idea is that a previously undetected planet with a mass several times that of Earth could be orbiting the Sun hundreds of times farther out than we do. The gravitational pull of such a distant giant would act like a cosmic shepherd, but a destructive one. Over billions of years, its repeated tugs on the orbits of distant Kuiper Belt objects would have thrown them into chaotic, unstable trajectories. Many would have been flung entirely out of the solar system into interstellar space, while others would have been sent plunging inward on long, elliptical orbits. The result would be a cleared-out zone, a gravitational cliff exactly where we see it, with only a handful of resilient objects remaining on strange, clustered orbits that themselves point to the potential presence of the unseen planet. The hunt for this hypothetical world is one of the most dramatic detective stories in modern astronomy, involving complex orbital calculations and painstaking scans of the sky to find a single, faint point of light moving imperceptibly slowly against the backdrop of fixed stars. Yet, Planet 9 is not the only possible culprit. Some scientists propose a less dramatic but equally fascinating alternative, that the early solar system's protoplanetary disk, the swirling cloud of gas and dust from which all the planets formed, simply had a sharp outer edge. Perhaps our young sun was born in a crowded stellar nursery, and a close pass by a sibling star long ago stripped away the outer material of the disk before it could coalesce into many objects. Or maybe the disk itself had inherent physical limitations, with conditions beyond a certain radius being unsuitable for the growth and retention of larger bodies. In this view, the Kuiper Belt Cliff isn't a feature that was carved out later. It's a fossilized boundary, a relic of the solar system's initial conditions preserved in ice for 4.5 billion years. Deciphering which of these stories is correct is an active area of research, and we have a dedicated investigator on the case. The New Horizons spacecraft, which gave us our first breathtaking close-ups of Pluto, is now venturing through this very region. As it travels farther into the Kuiper Belt, its sensitive cameras are constantly scanning, performing a direct census of the small objects in its path. Every new observation helps to constrain the models, telling us just how sparse the population truly is beyond the cliff. The data from New Horizons is crucial because it's looking for objects too small and faint to be seen easily from Earth. Each tiny world it discovers or fails to discover adds another piece to the puzzle. The mystery of the Kuiper Belt Cliff is more than just a question about a few distant ice balls. It is a direct probe into the violent history and ultimate architecture of our celestial neighborhood. Whether the answer is a hidden world or a primordial scar, Solving this riddle will force us to rewrite the final chapter of our solar system story, revealing the powerful, unseen forces that shaped our cosmic backyard. As we continue our journey into the cosmic unknown, we venture from the icy edges of our solar system back to the very dawn of everything, to a faint whisper of radiation that holds the blueprint for the entire universe. This is the cosmic microwave background, or CMB, the cool, ancient light that has been traveling for over 13 billion years, a fossilized snapshot of the universe when it was a mere infant, just 380,000 years old. It is the single most important piece of evidence we have for the Big Bang theory, and mapping its tiny temperature fluctuations, the hot and cold spots that represent the seeds of all future structure, has been one of the greatest triumphs of modern cosmology. The prevailing theory, built upon this data, rests on a foundational pillar known as the cosmological principle. This principle states that on the very largest scales, the universe is both isotropic and homogeneous. Isotropic means it looks the same in every direction you look, and homogeneous means matter is evenly distributed throughout space. There should be no special place, no center, and no preferred axis. The universe, in essence, should be a cosmic lottery, with structures forming from random quantum fluctuations stretched to cosmic proportions by inflation. So imagine the profound shock and disbelief when scientists, after creating the most detailed all-sky maps of this primordial light, discovered that the universe might be subtly pointing at us. This bizarre and unsettling finding has been dramatically nicknamed the axis of evil. The name itself evokes a sense of cosmic drama, and for good reason. When researchers analyzed the pattern of hot and cold spots in the CMB, they expected to find a perfectly random distribution, like the static on an old television tuned to a dead channel. Instead, they found a strange and unexpected alignment. The largest scale fluctuations in the ancient radiation appear to be oriented in a way that correlates, of all things, with the plane of our own solar system and the direction of the Earth's motion through space. It's as if the universe's oldest fingerprint has a pattern that somehow knows about our local cosmic address, a connection that should be astronomically impossible. This isn't just a minor curiosity, it strikes directly at the heart of the cosmological principle. If the universe has a preferred axis, a kind of cosmic equator, then the idea that we live in a universe without a center or a special direction begins to crumble. It suggests that either we are, against all odds, in a uniquely privileged position, or that the universe itself is not the random, isotropic expanse we have built our entire standard model of cosmology upon. The implications are so jarring that many physicists initially hoped it was just a statistical fluke, a coincidence that would vanish with more precise data. The pursuit of that precision led to one of the most advanced scientific instruments ever built, the Planck satellite. Launched by the European Space Agency, Planck was designed to map the CMB with unprecedented sensitivity and resolution, a mission that would either confirm the anomaly and plunge cosmology into crisis, or reveal it as an artifact of earlier, less accurate measurements. When the Planck team released their monumental dataset, the mystery only deepened. The alignment, though slightly less pronounced, stubbornly remained. The so-called axis of evil persisted in the most precise map of the early universe we have ever created. This forced the scientific community to confront the anomaly head-on, generating a spectrum of possible explanations that range from the mundane to the mind-bending. The most conservative, and for many the most hopeful, explanation is that of systematic error. Perhaps there is some unknown contamination in our measurements. One prominent candidate is foreground emission from within our own galaxy. The Milky Way is filled with dust and gas that also emits microwave radiation, and if our models for subtracting this galactic fog from the pristine CMB signal are even slightly imperfect, they could be imprinting a false pattern of alignment on the data. It's like trying to listen to a faint, distant symphony while standing next to a noisy highway. No matter how good your earplugs are, some of the local rumble might still seep through and distort the music. Researchers continue to painstakingly refine these foreground models, but so far, the alignment has proven resilient. If the effect is real and not an artifact, then we are left with explanations that would fundamentally reshape our understanding of reality. One extraordinary possibility is that the axis of evil is a cosmic scar, a remnant of the universe's conditions before the Big Bang. Some speculative theories of quantum gravity suggest that our Big Bang was not a true beginning, but rather a transition from a prior cosmic phase, perhaps a big bounce from a previous contracting universe. In such a scenario, the structure of that prior epoch could have imprinted a preferred direction onto our newborn cosmos, a kind of cosmic handed-down structure that breaks perfect isotropy. Another equally profound idea is that the alignment is evidence that our universe is not alone. The multiverse hypothesis, which posits that our cosmos is just one bubble in a vast, frothing sea of universes, could provide a mechanism. If our universe inflated from a tiny patch within a larger meta-universe, the shape and properties of that parent realm could have set a preferred orientation for our own cosmic bubble. In this view, the axis of evil might be a shadow on the cave wall, a hint of the greater structure that lies outside our observable horizon. The very name, axis of evil, reflects the deep discomfort this finding causes within the field of cosmology. It challenges our most cherished assumption that we are not special, and in doing so, it opens up a thrilling, if unsettling, frontier. Whether it is ultimately revealed as a sophisticated mirage caused by our own galactic environment, or as the first genuine crack in the foundation of the cosmological principle, its persistence serves as a powerful reminder that our models of the universe are not set in stone. They are living, breathing frameworks that must adapt to the data, no matter how inconvenient or bizarre that data may be. The axis of evil is not just a pattern in an ancient light. It is a question mark etched across the sky, asking us if we have the courage to follow the evidence, even if it leads to a universe far stranger than we ever imagined. From the grand, universe-spanning mystery of the cosmic microwave background, we now turn our attention to an object of breathtaking and intimate beauty, a celestial masterpiece whose precise geometry seems almost too perfect to be the work of random nature. Drifting through space about 2,300 light-years from Earth, in the constellation Monoceros, is a structure so striking it has been christened the Red Rectangle Nebula. At its heart lies a dying star, HD 44179, which is in the final stages of casting off its outer layers. This process creates what is known as a bipolar nebula, a common enough cosmic occurrence where gas and dust are ejected in two opposing directions, often forming an hourglass-like shape. But the Red Rectangle is no common nebula. When the Hubble Space Telescope turned its powerful eye toward it, it revealed a sight that left astronomers in awe. A series of stunning, ladder-like rungs forming a near-perfect X-pattern, all enveloped in a deep crimson glow. It looks less like a chaotic stellar death and more like a piece of cosmic architecture, a structure so geometrically precise it feels designed. The source of that intense red color is itself a fascinating piece of the puzzle. The rich hue doesn't come from the typical emission of glowing hydrogen gas, which paints many nebulae in pinks and reds. Instead, the red rectangle's color originates from a class of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. These are sprawling, carbon-based molecules, essentially the building blocks of soot, and they fluoresce with a distinctive red light when bathed in the intense ultraviolet radiation from the central star. The presence of these molecules in a region where a star is dying is a poignant reminder of the cosmic cycle of death and rebirth, as the raw materials for future chemistry, and perhaps even life, are seeded back into the galactic environment. But while the chemistry explains the color, it does nothing to solve the central, mesmerizing mystery. What carved this cosmic cloud into such an extraordinary shape? The prevailing theory focuses on the dynamic interplay at the very center of the system. HD 44179 is not a single star but a tight binary pair. Astronomers believe that as the primary star began its death throes, it started expelling its material outward. However, instead of flowing freely into space, this gas and dust became trapped in a dense disk of material that was likely created and shaped by the gravitational tug of war between the two orbiting stars. Imagine a spinning sprinkler spraying water in all directions, but then placing a large, flat donut around it. The water would be forced to escape only through the holes at the top and bottom, creating two opposing jets. This is the essential idea behind bipolar nebulae. In the case of the red rectangle, the dense disk is pinching the outflowing material into two powerful cones streaming out from the poles of the system. But this still only gets us to a simple hourglass. The breathtaking ladder rungs, the concentric squares that give the nebula its name, require another layer of explanation. The leading hypothesis is that the central binary system is acting as a kind of cosmic spray gun, but one with a pulsed output. As the two stars orbit one another every few hundred days, their gravitational interactions may cause periodic surges in the rate at which mass is ejected from the system. This would create a series of expanding bubbles or shells of gas, ejected in pulses rather than a steady stream. As these successive waves of material travel outward, they are funneled by the central disk into the two cone-shaped outflows. When we look at the nebula from the side, these expanding shells appear as the series of parallel rungs, creating the illusion of a three-dimensional ladder or a series of nested rectangles. The stunning X shape emerges because we are looking directly into the two hollow cones. The sides of the cones form the diagonal lines of the X, while the pulsed ejections create the horizontal rungs that connect them. Yet, for all the elegance of this model, it remains incomplete. Computer simulations that incorporate binary stars, accretion disks, and pulsed outflows can produce structures that are reminiscent of the red rectangle, but none have yet perfectly replicated the sharpness, the symmetry, and the precise spacing of those iconic rungs. There are other subtle complications. The alignment of dust grains by magnetic fields or the presence of shock waves where the fast-moving stellar wind collides with slower-moving ejected material could also be playing a role in sculpting the fine details. The red rectangle, therefore, stands as a beautiful challenge. It is a celestial phenomenon where we understand the basic ingredients, a binary star, a circumstellar disk, and pulsed ejections, but we have not yet mastered the full recipe. It serves as a humbling reminder that even when we have the right parts, the universe can assemble them with an artistry that still exceeds our predictive power. This cosmic tapestry, glowing with the red light of complex organic molecules, is more than just a pretty picture. It is a dynamic, evolving laboratory, a frozen moment in a slow-motion stellar ballet that continues to dare us to understand its every step. And from the beautiful geometry of a dying star, we travel to the outer solar system, where a different kind of geometric perfection has been whirling for decades, a shape so precise it seems to defy the very chaos of nature. High above the north pole of the ringed planet Saturn, a colossal, six-sided jet stream holds a storm in a form that would make any geometer do a double take. This is the Saturn hexagon, a cloud pattern wider than two Earths placed side by side, a 30,000-kilometer-wide atmospheric puzzle that has endured across multiple Saturnian seasons, outlasting every human mission sent to observe it. Imagine a hurricane so vast it could swallow our entire planet, but instead of a spinning, amorphous vortex, it's locked into the stark, sharp-angled form of a hexagon, with winds screaming along its walls at over 300 miles per hour. This isn't a fleeting cloud formation, it's a permanent planetary scale feature, a piece of celestial architecture etched into the atmosphere of a gas giant. The discovery of this bizarre structure came from the Voyager missions in the 1980s, but it was NASA Cassini spacecraft, which spent 13 years orbiting Saturn, that gave us our first detailed long-term look. Cassini's cameras revealed the hexagon not as a superficial cloud pattern, but as a deep-rooted jet stream, a wave of air propagating through the atmosphere like a ripple frozen in time. The most striking aspect is its unwavering stability. Earth's polar jet streams meander, buckle, and change shape with the seasons. Saturn's hexagon, by contrast, is rigid, maintaining its six-sided form with an almost mechanical precision as it rotates with the planet, completing one full revolution roughly every 10 hours and 30 minutes. This persistence is the core of the mystery. In a turbulent, gaseous environment where everything should be flowing and merging into circles or ovals, how does a straight-edged geometric shape not only form but hold its structure for decades and likely much longer? Scientists turn to the laboratory to crack this code, using the principles of fluid dynamics to simulate the conditions inside a gas giant's atmosphere. The key ingredient they found is rotation. In a famous set of experiments, researchers placed a cylinder of fluid on a rotating table. When they spun the inner cylinder faster than the outer one, simulating the different rotational speeds at various latitudes in an atmosphere, something remarkable happened. As they adjusted the speed differential, the fluid naturally began to organize itself into stable, standing waves. And at certain specific speeds, these waves took on distinct polygonal shapes, squares, pentagons, and yes, hexagons. This demonstrated that under the right conditions, the physics of a rapidly rotating fluid can naturally give rise to geometric patterns. The hexagon, in this view, is a type of Rossby wave, a planetary scale wave that gets trapped at a specific latitude, with its peaks and troughs creating the illusion of straight sides. The six-sided shape emerges as the most stable configuration for the particular conditions in Saturn's north polar region. But replicating the basic shape in a lab tank is one thing, fully explaining the Saturnian reality is another. The challenge lies in the staggering complexity of a real planetary atmosphere. Our simple lab models use uniform fluids, but Saturn's skies are a chaotic soup of hydrogen, helium, and various ices, with immense differences in temperature, pressure, and density from the cloud tops down to the deep interior. Computer simulations that try to incorporate all these real-world variables struggle to maintain a stable, long-lived hexagon. They often produce shapes that are close but not quite perfect, or hexagons that eventually break down or drift. The incredible stability of the actual phenomenon suggests there are deeper, more subtle factors at play that we haven't yet captured in our models. What is the precise role of the winds beneath the visible cloud tops? How does the planet's internal heat bubbling up from below influence the energy and stability of the wave? Is the hexagon a shallow weather pattern, or does it extend thousands of kilometers down into the planet's fluid interior, anchored by processes we cannot see? The hexagon is more than just a curiosity. It is a natural laboratory for understanding fluid dynamics on a scale we can never hope to recreate on Earth. By studying its stability and its interaction with smaller vortices that dance around its edges like moons around a planet, we learn fundamental truths about how energy moves and organizes itself in rapidly rotating systems. This knowledge doesn't just apply to Saturn. It informs our understanding of all fluid environments, from the great red spot on Jupiter to the vast ocean currents here on our own world. The enduring hexagon, therefore, stands as a humbling and elegant monument to the power of natural law. It shows us that the universe has an inherent leaning toward order, even within apparent chaos, and that the most alien and seemingly artificial sights can emerge from the simple, beautiful, and yet still incompletely understood dance of physics. But for all the grand structures and colossal forces we've encountered, some of the universe's most profound mysteries arrive not as vast nebulae or invisible planets, but as single, subatomic bullets fired from the depths of space. These are ultra-high-energy cosmic rays, and they represent an energy frontier so extreme it defies our understanding of physics itself. Imagine taking a proton, one of the fundamental particles in the nucleus of an atom, and accelerating it to a velocity just a hair's breadth from the speed of light. Now imagine imparting to that single tiny proton the kinetic energy of a professionally thrown baseball. This is not an exaggeration. These particles carry energies exceeding 100 million trillion electron volts, energies millions of times greater than what our most powerful machine, the Large Hadron Collider, can produce. Each one is a speck of matter carrying a macroscopic punch, the most energetic particle known to exist in nature. When one of these cosmic bullets slams into the top of Earth's atmosphere, it doesn't arrive quietly. It triggers a spectacular cascade, a sprawling avalanche of secondary particles called an air shower that can rain down over an area the size of a city. Detecting these events requires immense, ingenious observatories like the Pierre Auger Observatory in Argentina, which uses thousands of water tanks spread over 3,000 square kilometers to catch the faint flashes of light as these secondary particles pass through, or telescopes that watch for the faint ultraviolet glow the shower creates in the night sky. The detection itself is a triumph of human engineering, but it immediately presents a puzzle of cosmic proportions. What kind of natural particle accelerator in the universe could possibly be this powerful? The mystery deepens considerably when we apply our best theories of how the universe should behave. In the 1960s, physicists Kenneth Greisen, George A. Zatsepin, and Vadim Kuzmin independently calculated a fundamental speed limit for cosmic rays traveling across the universe. This theoretical boundary, now known as the GZK cutoff, arises from the fact that space is not a perfect vacuum. It is filled with the faint, relic photons of the cosmic microwave background, the afterglow of the Big Bang. For a proton with ultra-high energy, these serene background photons are no longer harmless. From the proton's point of view, thanks to the effects of relativity, these low-energy photons are massively blue-shifted, appearing as a relentless barrage of high-energy gamma rays. The proton can interact with these photons, and if the energy is just right, that collision can create new particles, specifically pions. This process saps the proton's energy, causing it to slow down. Over distances of more than 150 million light-years or so, this interaction should act as a cosmic barrier, preventing any proton from retaining its ultra-high energy. The universe, according to this well-established physics, should have a built-in energy ceiling for cosmic rays from distant sources. They should be eroded away long before they could ever reach our detectors on Earth. And yet, they do reach us. This is the heart of the enigma. We have consistently detected a small but significant number of cosmic rays that soar far above the predicted GZK cutoff. Their existence is a direct challenge, a clear signal that our understanding is incomplete. These particles are not just energetic, they are impossibly energetic given the vast distances we assume they have traveled. This forces astronomers into a frantic search for the culprits, for the cosmic engines capable of such unbelievable feats of acceleration. The suspects must be truly monstrous, events or objects that can generate forces far beyond the shock waves of a typical supernova. The shortlist includes some of the most violent phenomena known. Active galactic nuclei, the frenzied hearts of galaxies powered by supermassive black holes consuming vast amounts of matter, could potentially focus immense energy into particle jets. The mergers of neutron stars, cataclysmic events that shake the very fabric of space-time, are another candidate. Perhaps the most compelling suspects are gamma-ray bursts, the most energetic explosions in the universe since the Big Bang itself, which for a few brief seconds can outshine an entire galaxy. These events could, in theory, generate the required electromagnetic fields to whip a proton up to such insane energies. However, identifying the specific source for any given ultra-high-energy cosmic ray has proven to be incredibly difficult. Unlike light or gamma rays, cosmic rays are charged particles, and as they travel through the Milky Way's tangled magnetic fields, their paths are bent and scrambled. By the time one reaches Earth, it is impossible to simply trace its trajectory back in a straight line to its origin. It's like trying to find the source of a leaf blown into your yard during a hurricane. The path it took is far from direct. To make progress, scientists have to employ statistical methods, looking for clusters of these ultra-high-energy events on the sky map and hoping they point to a common direction. Some tantalizing hints have emerged, with a few events seeming to correlate with the locations of active galaxies or other energetic systems, but a definitive smoking gun has remained elusive. The sources appear to be rare, and the particles themselves are even rarer, with only a handful of the very highest energy events detected per square kilometer per century. This scarcity makes the detective work painstakingly slow. The puzzle is compounded by the fact that some of these ultra-high-energy particles might be heavier atomic nuclei, not just protons, which would interact with the background radiation differently and complicate the GZK picture even further. The mystery of ultra-high-energy cosmic rays is therefore a multi-layered one. We must first understand the unimaginable accelerators that create them, and then we must unravel the complex journey they undertake across a universe that, according to our best models, should have prevented them from ever arriving at our doorstep. Their very presence is a bold declaration that the most extreme reaches of our cosmos still hold secrets about the fundamental forces that govern matter, energy, and motion. But perhaps the most purely mind-bending of all cosmic riddles is one that plays out not in the vastness of space, but in the fundamental laws that govern reality itself. This is the black hole information paradox, a conflict so profound it pits the two pillars of modern physics, Einstein's theory of general relativity and the strange rules of quantum mechanics, against each other in a battle with the very nature of truth at stake. To grasp this paradox, we first need to understand what physicists mean by information. It's not just books or hard drives. In this context, information refers to the specific, unique identity of every particle that falls into a black hole. Think of it this way: if you burn a book, you might think the information is destroyed, but in reality, a hypothetical superintelligence could, in principle, collect every single smoke particle, measure every photon of light, and trace the heat dissipating into the air to perfectly reconstruct the original book. Quantum mechanics insists that this kind of perfect reversibility is a fundamental law of the universe. Information is never truly lost, it just gets scrambled and spread out. It's a cosmic promise that the past is always, in some form, preserved. Now enter the black hole as described by general relativity. Its boundary, the event horizon, is a point of no return. Once anything, a star, a spacecraft, or a hapless astronaut crosses this threshold, it is irretrievably lost to our universe. The intense gravity pulls everything inward toward the central singularity, a point of infinite density where the known laws of physics completely break down. For decades, this was the accepted, if unsettling, picture. Black holes were the ultimate cosmic shredders, and the information about what fell into them was gone forever. But then, in the 1970s, Stephen Hawking made a revolutionary discovery. He realized that by applying quantum theory to the space just outside the event horizon, a black hole isn't completely black. Due to weird quantum fluctuations in the vacuum of space, pairs of virtual particles constantly pop in and out of existence. Normally, these particles annihilate each other almost instantly. But right at the edge of a black hole, something strange can happen. One particle of the pair might fall in while the other escapes into space. The particle that escapes carries away a tiny amount of energy, and to conserve energy, the black hole itself must lose a correspondingly tiny bit of mass. This is Hawking radiation. Over incredible spans of time, this process causes the black hole to slowly evaporate, eventually vanishing entirely in a final faint puff of radiation. And this is where the paradox ignites. The Hawking radiation that leaks out is entirely random, determined only by the black hole's mass, charge, and spin. It carries no information whatsoever about the specific things that formed the black hole or fell into it. It's like burning that book, but instead of smoke and ash that could theoretically be reassembled, you get only a featureless, uniform heat. So, when the black hole has completely evaporated, what happened to the information about the original star, the spacecraft, and the astronaut? According to general relativity and Hawking's original calculation, it has been utterly erased from existence. But according to the unwavering laws of quantum mechanics, this is absolutely forbidden. We are left with a catastrophic contradiction. One of our two most successful theories of physics must be wrong. Either general relativity fails in its description of black holes, or quantum mechanics' sacred principle of information conservation is flawed. This isn't just a technical debate, it's a crisis at the very foundation of our understanding of reality. The quest to resolve this paradox has pushed theoretical physics into some of the most speculative and astonishing territories ever conceived. One of the most influential ideas is the holographic principle. This mind-boggling concept suggests that all the information about everything that falls into a black hole is not lost inside, but is instead encoded in a scrambled, two-dimensional form on the surface of the event horizon, like a cosmic fingerprint. Think of it as the universe's ultimate data compression. When you watch a 3D hologram, the image has depth and volume, but all the information needed to create it is stored on a flat 2D surface. In the same way, the holographic principle proposes that our perception of a three-dimensional world falling into a black hole is really just a projection of information stored on its two-dimensional boundary. When the black hole evaporates via Hawking radiation, this information on the surface is somehow transmitted or imprinted onto the escaping radiation, preserving it. In this view, the black hole isn't a destroyer of information, but the ultimate supercomputer, performing an unimaginably complex calculation that encodes and eventually returns the information it consumed. Another compelling solution suggests that black holes don't just vanish. Instead, they might evaporate down to a tiny, stable remnant, no larger than a grain of sand but containing all the information of everything that ever fell in, locked away forever. Or perhaps the information does slowly leak out with the Hawking radiation, but in such a horribly scrambled and chaotic form that it is effectively impossible to decode, like trying to reconstruct a library from the ashes of a fire scattered across a continent. Some physicists, like Hawking himself, eventually came to believe in this soft-hair approach, where subtle imprints on the event horizon allow information to be preserved. The debate is so intense that it has even led to scientific bets, with Hawking famously conceding one to physicist John Preskill, admitting that information probably does escape. Yet, despite decades of brilliant work, no single solution has achieved universal consensus. The mathematics involved is ferociously complex, and a complete theory that successfully merges general relativity with quantum mechanics, a theory of quantum gravity, remains the holy grail of physics. The black hole information paradox is more than an abstract puzzle for theorists. It is a direct window into the next great revolution in science. It forces us to ask what reality truly is at its most fundamental level. Is the universe at its heart a deterministic system where every event can be traced back to a cause? Or are there places like black holes where causality itself breaks down and the past is truly erased? Solving this paradox wouldn't just tell us what happens to stuff that falls into a black hole. It would reveal the deepest operating system of the cosmos, rewriting our understanding of space, time, and information forever. Now, let's rewind the cosmic clock all the way back to the universe's first few minutes. a time of almost unimaginable heat and density when the entire cosmos was a seething nuclear furnace. In this primordial cauldron, the first atomic nuclei were forged in a process called Big Bang nucleosynthesis. For the most part, our theoretical models of this epic event are a spectacular success. They predict with stunning accuracy the observed cosmic abundances of the lightest elements, the vast amounts of hydrogen, the significant portion of helium, and even the tiny traces of deuterium and helium-3. These predictions matching observations so perfectly is one of the strongest pillars of evidence for the Big Bang theory itself. Yet, nestled within this triumphant story is a single, stubborn anomaly, a small but significant failure that has resisted explanation for over 50 years. This is the cosmological lithium problem. The issue is startlingly specific. According to our most sophisticated models, which incorporate the known laws of nuclear physics and the measured density of ordinary matter, a specific isotope known as lithium-7 should have been created in a particular amount during that initial forging. Lithium-7 is the stable, lighter cousin of the metal we use in our batteries. The models tell us we should be able to find it in the atmospheres of the universe's oldest stars, which formed from nearly pristine gas shortly after the Big Bang. These ancient stellar relics are like cosmic time capsules. Their composition reflects the chemical makeup of the early universe before later generations of stars had a chance to pollute the mix with heavier elements. So, astronomers point their telescopes at these venerable stars and carefully measure the lithium content. And time after time, across many different stars, they get the same baffling result. The amount of lithium-7 they observe is only about 1/3 of what the models insist should be there. It's a discrepancy that cannot be brushed aside. It means that our otherwise flawless understanding of the universe's first few minutes is missing a crucial piece of the puzzle. This seemingly minor accounting error has major implications, prompting physicists to explore solutions that range from the subtle to the revolutionary. One line of investigation questions whether our knowledge of the nuclear reactions themselves is complete. The primordial nucleosynthesis process involved a complex dance of particles colliding and fusing, and the predicted final abundance of lithium is exquisitely sensitive to the precise rates of a few key reactions. Perhaps there is a previously unknown nuclear resonance, a fleeting, energetic state that makes certain reactions proceed faster or slower than we've calculated in our laboratories. If a reaction that destroys lithium were slightly more efficient or one that creates it were slightly less efficient, it could potentially resolve the mismatch. However, despite decades of refined experimental work, no such definitive nuclear physics solution has emerged to fully close the gap. Another fascinating possibility ventures beyond the standard model of particle physics. What if entirely new, hypothetical particles were present in the early universe, subtly altering the conditions of the nuclear furnace? A leading candidate is a type of particle known as a dark photon, a force carrier for a hypothetical dark sector that could interact weakly with ordinary matter. In the intense heat of the first few minutes, these particles could have been produced and then decayed, injecting extra energy into the primordial plasma. This would have slightly changed the density and temperature at which nucleosynthesis occurred, potentially reducing the final yield of lithium-7 without messing up the otherwise perfect predictions for hydrogen and helium. It's an elegant idea, but one that so far lacks direct experimental confirmation. Then there are the stellar astrophysicists who propose that the models are correct and the lithium was indeed created in the predicted amount, but it was subsequently destroyed in the very stars we now use to measure it. Stars, even old ones, are not perfectly static containers. They have convection currents that can drag material from the surface down into the hotter interior, where temperatures are high enough to burn and destroy lithium. If these ancient stars have a different internal structure or rotation rate than we assume, they could have depleted their surface lithium over billions of years, giving us a falsely low measurement. The challenge here is that we observe a remarkably consistent lithium abundance in many different old stars, which would require a universal and finely tuned destruction mechanism to explain. Furthermore, the problem is even trickier for the other lithium isotope, lithium-6. Some observations suggest that the oldest stars contain more lithium-6 than the standard Big Bang model predicts, which is the opposite problem and even harder to explain with stellar destruction, as lithium-6 is actually more fragile and easier to destroy than lithium-7. This persistent puzzle, this tiny crack in the foundation of our cosmic origin story, serves as a powerful reminder of the scientific process. It shows that even our most successful theories can harbor unresolved tensions. The lithium problem is not large enough to topple the Big Bang model, but it is precisely the right size to act as a probe, pointing us toward new physics we might otherwise have missed. Whether the ultimate answer lies in a refined nuclear reaction rate, a novel particle from the dark sector, or a deeper understanding of stellar evolution, solving it will give us a cleaner, more complete picture of the universe in its fiery infancy. After more than half a century, this small deficit of a light metal continues to be a heavyweight challenge for cosmologists. After confronting the paradoxes of black holes and the lingering questions from the universe's first moments, we arrive at a celestial marvel that looks less like a natural formation and more like a piece of divine geometry. Drifting through the cosmos 600 million light-years away in the constellation Serpens is a galaxy so perfectly structured it could have been crafted by a cosmic jeweler. This is Hoag's object, and to gaze upon its Hubble Space Telescope image is to witness something that feels almost too perfect to be real. At its heart lies a brilliant, dense core of aging yellow stars, glowing with the warm light of countless ancient suns. Encircling this core is a flawless, ethereal ring of vibrant, young blue stars, a perfect circle of stellar nurseries and brilliant new life, and between them, a gap, a vast, profound, and eerily empty chasm of near-total darkness, a cosmic moat separating the core from the ring with a precision that defies our standard notions of how galaxies behave. This celestial bullseye presents an immediate and profound challenge to one of the most fundamental tools in astronomy, galaxy classification. For decades, we've sorted the island universes of the cosmos into a simple, elegant scheme. There are spiral galaxies like our own Milky Way with their graceful, winding arms of stars and gas. There are elliptical galaxies, amorphous blobs of older stars, the retired giants of the universe. And then there are the irregulars, the chaotic, misshapen results of galactic collisions and close encounters. Hoag's object fits into none of these categories. It is not a spiral, it has no central bar, no winding arms spiraling out from its core. It is not an elliptical. Its distinct, separated ring is a feature of dynamic youth, not serene old age. It stands utterly alone, a singular cosmic masterpiece that seems to have written its own rulebook, leaving astronomers to ponder how such a perfectly isolated ring of starlight could ever come to be. The most intuitive and widely explored theory points to a violent, transformative event in the deep past, a galactic collision. The concept, known as the density wave theory, suggests that billions of years ago, a smaller galaxy might have plunged directly through the heart of what was then a more ordinary spiral disk. Such a catastrophic encounter would have sent immense ripples, shockwaves of gravitational force racing outward through the victim galaxy's gas and dust. Just as a pebble dropped in a pond creates an expanding ring of waves, this intergalactic trespass could have compressed the galactic material into a single, intense wave of density. In the wake of this wave, the vast clouds of gas would have collapsed under their own gravity, igniting a firestorm of new star formation in a perfectly circular ring, while leaving the central core of older stars relatively undisturbed. The intruder galaxy, having delivered its transformative blow, would have continued on its way, leaving behind this beautiful, ringed scar as the only evidence of its passage. This process is not entirely theoretical. We see other, messier, ring galaxies like the Cartwheel Galaxy that fit this narrative quite well. However, Hoag's object presents a problem for this tidy story. It is incredibly symmetrical and serene, showing none of the twisted, disrupted patterns or lingering companion galaxies that usually betray such a violent history. The perpetrator is gone without a trace, and the ring itself is almost impossibly pristine. This has led to the consideration of a more internal, self-generated origin. Another compelling hypothesis suggests that Hoag's object could be the rarest of phenomena, a spontaneously formed ring galaxy, emerging from a primordial instability within a vast disk of stars and gas. In this scenario, a tremendously massive and extended disk of material could, under the right conditions, become gravitationally unstable. The disk would not be able to hold its form and would instead naturally fragment, with its outer regions pulling away to form a distinct ring while the central material condensed into a tight core. This process, known as a resonance-driven ring, wouldn't require a collision at all. It would be a galaxy born from its very inception with this perfect partitioned structure. Yet this model, too, struggles to fully capture the reality of Hoag's object. The utter emptiness of the gap between the core and the ring is a particular challenge. If the ring formed from the galaxy's own disk, we might expect to see at least a faint smattering of stars, a dusty veil of material connecting the two components. Instead, we see a clean, sharp division, a void that appears to have been deliberately swept clear of all stellar matter. The mystery is compounded by another astonishing discovery. Peering even deeper into the void around Hoag's object, astronomers have spotted another, much fainter ring galaxy, a perfect cosmic echo lying far in the background, directly behind the gap of the first. This chance alignment, a ring behind a ring, only heightens the sense of awe and perplexity. It feels like a cosmic wink, a hint that perhaps these structures are not quite as impossibly rare as we once believed, but that their formation is governed by a physics we have yet to fully comprehend. Hoag's object, therefore, is more than just a beautiful anomaly. It is a profound challenge to our models of galactic evolution and stability. It asks us whether our reliance on violent collisions to explain all unusual structures has blinded us to more subtle, internal processes that can sculpt a galaxy with the precision of a master craftsman. It stands as a silent, perfect circle in the void, a question mark written in starlight, daring us to understand how such serene and perfect isolation could ever arise from the chaotic, turbulent forces that typically govern the birth and life of galaxies. Now we turn our focus from the grand, cosmological scale to a world much closer to home, a planet that has captivated human imagination for centuries. Mars, our rust-colored neighbor, has been scrutinized by orbiters and rovers for decades, and we have mapped its surface in exquisite detail. We know its mountains are the tallest in the solar system and its canyons the deepest. Yet, one of its most compelling mysteries is not something we can see, but something we have only just begun to sniff out in the thin, cold Martian air. This is the enigma of Martian methane, a gas that shouldn't be there, appearing and vanishing like a ghost, and its presence raises one of the most profound questions we can ask. Could this be a sign of life? The significance of methane on Mars is profound because of what it represents here on Earth. In our own atmosphere, the vast majority of methane is biologically produced. It is a waste product of methanogenic archaea living in the guts of cows, in wetlands, and deep underground. It is also a key signature of our industrial activity. While methane can be produced by purely geological processes, its detection on another world immediately puts the possibility of biology on the table. Finding it on Mars is like smelling smoke in a forest. It doesn't automatically mean there's a campfire, but it certainly makes you start looking for one. The first tentative whiffs came from Earth-based telescopes and early orbiters, but the mystery truly deepened with the arrival of NASA's Curiosity rover in 2012. Nestled within Gale crater, the rover's sample analysis at Mars Instrument, a sophisticated onboard chemistry lab, has repeatedly detected methane. But it doesn't behave like the steady, predictable methane seepage we might expect. Instead, the gas appears in sudden, short-lived spikes, with concentrations sometimes soaring to 10 times the background level before vanishing completely within a matter of hours or days. This sporadic nature is the first major piece of the puzzle. It suggests that whatever is producing the methane is a localized and transient process, a source that turns on and off, and one that is being quickly destroyed by the Martian environment. This leads directly to the second great challenge. The methane is being destroyed far faster than our models can explain. The thin Martian atmosphere is bathed in ultraviolet radiation from the sun, and this radiation should quickly break methane molecules apart, giving them a lifespan of several hundred years. The fact that Curiosity sees plumes appear and disappear over just a few Martian days implies there is an additional, incredibly efficient destruction mechanism at work right now that we do not understand. It's as if a candle were lit in a sealed room, but the flame is snuffed out in seconds by something unseen in the air. This rapid destruction means that any methane we detect must have been released very recently, pointing to an ongoing, active process somewhere in the vicinity. The plot thickened further with the arrival of the ExoMars Trace Gas Orbiter, a European-Russian mission specifically designed to conduct a precise, global census of trace gases in the Martian atmosphere. Equipped with state-of-the-art spectrometers, it can scan the entire planet from orbit. Yet, in a baffling contradiction, the orbiter has, for the most part, reported a stunning lack of methane on a global scale. This creates a stark conflict between the rover's ground-level sniffs and the orbiter's bird's-eye view. How can Curiosity be sitting in a cloud of gas that the orbiter flying overhead cannot see? One possibility is one of timing and scale. The Trace Gas Orbiter might simply be missing these brief, localized plumes. If the methane is released in small, quick bursts and then destroyed almost immediately, the orbiter could easily pass over the wrong place at the wrong time. Another, more complex idea involves the time of day. Curiosity's measurements are often taken at night when the Martian boundary layer, the lowest part of the atmosphere, is calm and stable. The orbiter, however, makes its measurements during the daytime when solar heating creates turbulence and mixing, which could disperse and dilute the methane so thoroughly that it falls below the orbiter's detection threshold. This would mean the Martian night is hiding a secret that the daytime sun scatters to the winds. This discrepancy isn't a failure of science, it's the mystery itself, forcing a deeper investigation into the complex and still poorly understood chemistry and circulation of the Martian atmosphere. So, if the methane is real and local, where is it coming from? Scientists are pursuing two main lines of investigation, one that points to the rocks and one that points to the fantastical. The leading geological explanation is a process called serpentinization. This occurs when certain types of iron and magnesium-rich rocks, like olivine, come into contact with water in a low-oxygen environment. The chemical reaction between the rock and water produces a family of minerals called serpentines, and as a byproduct, it can release hydrogen gas. This hydrogen can then react with carbon dioxide in the atmosphere through another process to create methane. We see this happen on Earth in places like the Lost City hydrothermal field at the bottom of the Atlantic Ocean. On Mars, this would imply that liquid water, at least in the form of briny groundwater, is still interacting with bedrock deep underground and occasionally venting the resulting methane to the surface through cracks and fissures. This is a completely abiotic, non-living process, yet it would still be a revolutionary discovery, revealing that Mars is a geologically active world with hidden reservoirs of water. Then, of course, there is the biotic possibility, the tantalizing, pulse-quickening idea that the methane is a metabolic waste product of living organisms. These wouldn't be the little green men of science fiction, but most likely microscopic methanogens, simple microbes similar to those that thrive in extreme environments on Earth, deep underground or in anaerobic environments. They consume hydrogen and carbon dioxide and exhale methane. The case for this is built on analogy with Earth. We find life in the most inhospitable places on our planet, from deep gold mines to subterranean lakes in Antarctica. If life ever did arise on a warmer, wetter Mars billions of years ago, it's conceivable that some microbial colonies retreated underground, finding refuge in aquifers deep beneath the frozen surface, where they could persist to this day, their faint metabolic activity occasionally bubbling up to the surface as a methane plume. This is the heart of the mystery's power. A single, simple gas, CH4, sits at the crossroads of geology and biology. Its detection is not a smoking gun for life, but it is the most compelling chemical whisper we have yet heard, a hint that the dry, dusty world we see today might be hiding a secret, wet, and potentially living interior. Solving the Mars methane mystery is therefore one of the primary objectives for current and future missions. It requires understanding the complex atmospheric chemistry that destroys it, pinpointing the exact locations of its release, and ultimately determining its origin. Is it the breath of a geochemical process, or could it just possibly be the faint, enduring signature of life next door? After delving into the chemical whispers of Mars, we now journey into a realm of physics so abstract and bizarre that it challenges our very definition of what a particle is. This is the world of unparticle physics, a highly speculative but mathematically elegant theory proposing the existence of a hidden sector of reality that operates under rules completely foreign to our own. Imagine if you could take all the familiar building blocks of the universe, the electrons, the quarks, the photons, and then discover that they are just one part of a much larger and weirder picture. Unparticle physics suggests just that, positing a shadow universe, a sector composed of fields that are scale invariant. To understand what that means, consider an ordinary particle like an electron. It has a specific mass and a definite identity, but a scale-invariant field has no fixed mass scale. It looks the same and behaves the same no matter how much you zoom in or out on it. It doesn't manifest as distinct, countable particles, but rather as a continuous, ethereal substance that doesn't fit into our standard particle zoo. The term unparticle captures this perfectly. It's stuff that doesn't behave like any particle we know. The theoretical foundation for this mind-bending idea was laid in 2007 by the physicist Howard Georgi. He proposed that at very high energies, there could exist a set of fields that interact with our familiar particles only through extraordinarily feeble forces. As the universe cooled from the Big Bang, this hidden sector would undergo a phase transition, emerging not as a collection of particles with specific masses, but as a scale-invariant, unparticle stuff. How would this strange substance actually behave? A useful, though imperfect, analogy is to think of a cloud. You don't count the number of cloud particles in a nebula, you describe it by its density and its texture. An unparticle cloud would interact with matter in ways that seem to violate our standard conservation laws. For instance, when a conventional particle decays, the energy and momentum of the products add up in a predictable, quantized way. But if that decay occasionally produced a puff of unparticle stuff, the energy distribution of the remaining ordinary particles would look bizarre and smeared out, as if some energy had simply leaked away into this hidden sector without a clear trace. This is where the tantalizing connection to unexplained phenomena comes in. While unparticle physics remains a fringe idea, a handful of puzzling anomalies in high-energy experiments have been put forward as potential, though highly tentative, signatures. Over the years, certain particle collisions at facilities like the Large Hadron Collider have shown slight statistical excesses or unexpected patterns in the energy of their decay products, deviations so small they could easily be background noise, but which are difficult to explain within the standard model. Similarly, in the realm of astrophysics, the precise properties of the cosmic microwave background or the cooling rates of certain neutron stars have features that are perfectly consistent with known physics, but for which unparticle interactions have been explored as a remote alternative explanation. The key point is that these are not discoveries, but rather intriguing what-if scenarios. Proponents of the theory scrutinize these minor data glitches, asking if they could be the faint, first fingerprints of an unseen sector of reality, making its presence known at the energy and distance frontiers. The implications of confirming such a theory would be nothing short of revolutionary. It would mean that the fundamental forces and particles we have so painstakingly catalogued are merely the tip of a vast hidden iceberg. Our entire understanding of matter and energy would need a profound rewrite. The universe would be revealed to contain a form of stuff that is fundamentally amorphous, without a fixed mass or discrete identity, yet capable of interacting with our world and influencing its evolution. It would open a portal to a whole new world of physics with potential connections to dark matter, dark energy, and the very unification of all forces. For now, unparticle physics stands as a brilliant exercise in theoretical imagination, a stark reminder that our current models, for all their success, may be just a small part of a much stranger and more wondrous cosmic story. It represents the ultimate scientific gamble, the search for a phenomenon so alien that it doesn't even fit our current definition of what a phenomenon is. Just when we thought we had a handle on the dominant role of dark matter in the cosmos, the universe presented us with a paradox so baffling it seemed to break its own rules. For decades, the existence of dark matter had moved from a controversial hypothesis to a foundational pillar of cosmology. We saw its gravitational hand in the rapid orbits of stars within galaxies and the warping of light around massive clusters. The conclusion felt inescapable. Dark matter is the invisible scaffolding upon which all galaxies are built. It provides the necessary gravitational glue to gather ordinary matter and ignite the birth of stars. So, imagine the collective shock when astronomers, using a combination of the Hubble Space Telescope and the Keck Observatory, stumbled upon a galaxy that appeared to be missing this fundamental ingredient. This ghostly collection of stars, known as NGC 1052 DF2, looked unlike any spiral or elliptical we had seen before. It's what's known as an ultra-diffuse galaxy, a vast, wispy expanse where stars are scattered so thinly that you can practically see right through it to the galaxies beyond. But its ethereal appearance wasn't the real surprise. It was what was missing that sent ripples through the astrophysics community. The method for uncovering this absence was elegantly simple, relying on the same principles that first revealed dark matter's presence. Astronomers measured the motions of 10 luminous globular clusters, dense balls of stars orbiting within the galaxy. According to Newton's laws of motion, the speed at which these clusters move is a direct gauge of the total gravitational pull they are experiencing, which comes from the combined mass of all the visible stars plus any unseen dark matter. In a typical galaxy, the clusters whip around at speeds that can only be explained if a massive halo of dark matter is enveloping the system. But in NGC 1052 DF2, the results were stunningly different. The globular clusters were moving remarkably slowly. In fact, their velocities were perfectly in line with the gravitational pull you would expect from the galaxy's visible stars alone. There was no extra pull, no sign of an unseen mass yanking them along. The inescapable conclusion was that this galaxy, against all odds and expectations, contained little to no dark matter. This discovery flipped the entire narrative on its head. Finding a galaxy without dark matter is, in its own way, just as profound as proving dark matter exists. Think of it like this: if someone claimed that all houses are built on concrete foundations, and you then found a beautiful, fully formed house simply floating in the air with no foundation at all, you would be forced to question your understanding of how houses are built. That's the precise conundrum DF2 created. It acts as a crucial controlled experiment. For years, a small but persistent minority of scientists had argued that perhaps we don't understand gravity correctly, and that what we call dark matter is actually a modification of the laws of physics on large scales, a theory known as modified Newtonian dynamics or MND. But DF2 delivers a devastating blow to that idea. If the observed motions of stars and clusters were due to a modified law of gravity, then every galaxy should exhibit the same kind of anomaly. The fact that DF2 behaves exactly as Newton and Einstein predict without dark matter is powerful evidence that dark matter is indeed a real, tangible substance, a substance that can, for some mysterious reason, be separated from the galaxies it supposedly helps to create. So how does a galaxy form without this cosmic scaffolding? The leading theory points to a violent, intergalactic divorce billions of years in the past. NGC 1052 DF2 is not isolated. It lives in the gravitational domain of a massive elliptical galaxy called NGC 1052. Astronomers hypothesize that long ago, this dominant neighbor may have played the role of a cosmic thief. During a close encounter or a merger event, vast streams of gas and stars could have been violently stripped away from a smaller galaxy. In this chaotic process, the dark matter, which interacts only through gravity and not with itself, would have been pulled away one way, while the collisional ordinary gas and dust were captured by the larger galaxy. What remained was a shred of pure, bare baryonic matter, a galaxy born from the wreckage of a cosmic collision. Essentially, DF2 might be the ghostly echo of a much more substantial galaxy that was picked apart, leaving behind only the stars that managed to cling together. This is a radically different formation path from the slow, steady accumulation within a dark matter halo that we typically envision. The plot, however, has only thickened since that first discovery. Other candidate galaxies lacking dark matter have been identified, but the field was rocked when some of the initial distance measurements for DF2 were called into question. If the galaxy was actually closer than first thought, its stars would be intrinsically dimmer, meaning there is less ordinary matter present, which would then require the presence of dark matter to explain the observed motions. This triggered a fierce and healthy scientific debate, with different teams using different methods to pin down the galaxy's true distance. The most recent and precise measurements, painstakingly conducted with Hubble, have strongly reaffirmed the original distance, solidifying the case that DF2 is indeed a galaxy profoundly deficient in dark matter. This back and forth is science at its best, a relentless pursuit of precision that ultimately strengthens the extraordinary conclusion. The existence of even a single confirmed galaxy without dark matter forces a dramatic expansion of our theories. It tells us that the universe has more than one recipe for building a galaxy. Some are sculpted by the gentle accumulation within dark matter halos, while others, it seems, can be forged in the violent fires of galactic interaction, born from chaos and stripped of their dark essence. This paradox doesn't dismantle the dark matter paradigm. Instead, it enriches it, revealing a cosmic diversity far greater than we had ever imagined. And now we turn our gaze inward to the very heart of our cosmic home, only to discover that our own Milky Way galaxy has been keeping a colossal secret. For billions of years, two immense, ghostly orbs have been ballooning out from the galactic center, stretching for 25,000 light-years above and below the galactic plane. These are the Fermi bubbles, and their discovery was a complete surprise, hidden in plain sight until the Fermi Gamma Ray Space Telescope began scanning the sky in 2008. What it revealed was not a gentle, uniform glow, but a pair of gigantic, lobe-like structures glowing fiercely in high-energy gamma rays, like two cosmic lungs inflated with pure power. They are so vast that if our eyes could see their faint, high-energy light, they would dominate half of the night sky, a silent, brooding monument to a cataclysm we entirely missed. Later observations in X-rays by the E-Rosetta telescope confirmed and expanded this picture, revealing the bubbles have a complex, almost soap bubble-like structure filled with incredibly hot, turbulent gas. These are not empty voids, they are colossal balloons of energetic plasma, cosmic rays, and magnetic fields, a pair of titanic relics from a violent eruption that occurred right in our own backyard. The sheer scale of these bubbles immediately points to an energy source of almost unimaginable power. To inflate structures this large requires a blast equivalent to the simultaneous explosion of millions of supernovae. The prime suspect, almost by default, is the supermassive black hole that lurks at the very center of our galaxy, Sagittarius, a star. For now, our central black hole is a quiet, lethargic beast, only nibbling on the occasional cloud of gas. But the Fermi bubbles are undeniable evidence that this slumbering giant was once awake and ferociously active. The leading theory is that we are witnessing the aftermath of a past, active galactic nucleus event. This could have happened in one of two spectacular ways. Perhaps Sagittarius, a star, experienced a period of intense feeding, pulling in a vast amount of gas and dust from its surroundings. As this material swirled into an accretion disk heated to millions of degrees, it could have launched two powerful, opposing jets of plasma and radiation directly along its rotational axis. These jets would have punched through the galactic gas, inflating the bubbles as they expanded outward. Alternatively, the black hole might have undergone a different kind of outburst known as a quasar wind. In this scenario, the intense radiation pressure from the feasting black hole itself creates a powerful, spherical gale that blows material outward in all directions, which then gets focused and channeled by the thick disk of the galaxy into a bipolar structure. Pinpointing exactly when this celestial fireworks display occurred is a detective story in itself. By studying the expansion rate and the cooling of the gas within the bubbles, astronomers have made a rough estimate, suggesting the eruption happened sometime between 6 and 26 million years ago. That may sound like an ancient event, but on a galactic timescale, it's a relatively recent occurrence. To put it in perspective, this eruption was happening while early ancestors of humanity were already walking the Earth. The energy required is staggering, demanding that our supermassive black hole must have briefly shone with the power of 100 million suns. This forces a profound revision of our galaxy's history. We often think of the Milky Way as a stable, serene spiral, but these bubbles reveal a past punctuated by violent, explosive chapters. Our galactic center is not a permanently quiet place. It has a temper capable of unleashing destructive forces that reshape its entire structure and influence the conditions for star formation across tens of thousands of light years. However, the exact mechanism behind this great eruption remains a subject of intense debate. The clean, jet-driven model is elegant, but some observations suggest the bubbles are fatter and more spherical than a typical jet would create, favoring the quasar wind hypothesis. Others have proposed even more exotic possibilities. Could the bubbles have been formed not by a single cataclysmic event, but by a series of smaller, repeated outbursts from Sagittarius, a star, over millions of years? Or, moving beyond the black hole entirely, could they be the accumulated result of a period of frenzied star formation at the galactic center, where the combined winds and supernova explosions from millions of massive stars collectively blew this enormous structure? While this stellar explanation is possible, the incredible symmetry and focused energy of the bubbles make the black hole the more compelling culprit. The ongoing study of the Fermi and E-Rosetta bubbles is like reading a cosmic history book written in gamma rays and X-rays. Their structure, temperature, and composition hold the clues to the nature of that long-ago explosion. They stand as a humbling reminder that even our own galaxy, which we have mapped and studied for centuries, can still reveal monumental secrets, forcing us to confront the fact that the quiet cosmic neighborhood we see today is built upon a foundation of unimaginable ancient violence. But if the Fermi bubbles represent a slow, monumental release of energy from our galactic center, then the next phenomenon shows us the instant, catastrophic violence that occurs when a black hole decides to feast. We now witness one of the most extreme events in the cosmos, a stellar death so brutal it defies imagination, a tidal disruption event. This occurs when an unlucky star wanders too close to the immense gravitational pull of a supermassive black hole. The force of gravity on the side of the star nearest the black hole is so much stronger than the force on the far side that the entire star is stretched and compressed, not just spaghettified in theory, but literally ripped apart in a single ferocious episode. The star is shredded into a long, thin stream of gas, about half of which is flung away into the darkness, while the other half swings back around to form a seething, hot accretion disk around the black hole. This disk of stellar debris, heated to temperatures of millions of degrees, then begins to glow with an intense flare of light across the electromagnetic spectrum, from visible and ultraviolet to high-energy X-rays, often outshining the entire host galaxy for a few brief, brilliant months. These events are the universe's most dramatic way of signaling that a black hole has just had a meal. In 2014, the All-Sky Automated Survey for Supernova, a network of small telescopes designed to find exploding stars, spotted one such flare in a galaxy about 290 million light-years away. It was named Assassin 14 Lie, and at first it seemed to be a textbook example of a tidal disruption event. Astronomers watched as a supermassive black hole with a mass of about 2 million times that of our Sun tore apart a star that had ventured too close. They saw the initial flash, the rise to peak brightness, and they began tracking its slow fade, expecting it to follow the standard script. According to our best models, as the gaseous debris from the star swirls inward, it should be rapidly consumed by the black hole. The accretion disk should be a transient thing, forming quickly and then draining away almost as fast, its brilliant light fading over a period of months as the last of the stellar material vanishes across the event horizon. The X-ray emission coming from the hottest, innermost regions of the disk should be the first to vanish as the fuel supply is exhausted, but Assassin 14 Lie refused to follow the script. Years after the star was destroyed, long after the visible light had faded, something astonishing happened. The X-ray emission, which should have been the first to disappear, not only persisted but remained remarkably stable and strong. This was not a faint, dying ember. It was a steady, unwavering beacon of high-energy light, continuing to shine with undiminished power for years on end. It was as if a campfire, after burning down to ash, suddenly decided to keep producing a roaring, consistent flame without any more wood. This bizarre persistence posed a direct challenge to the established theory of how these events unfold. Our models suggested that the inflow of matter should be a rapid, one-time affair. The enduring X-ray signal from Assassin 14 Lie, however, pointed to a continuous, long-term energy source, a reservoir of hot gas that was somehow being replenished or sustained far longer than anyone thought possible. This forced a radical rethink of the entire physics at play in the immediate vicinity of the black hole. One leading hypothesis suggests that the initial tidal shredding of the star was not the end of the story, but merely the beginning of a more complex and drawn-out process. Perhaps the stream of stellar debris did not all fall in at once. Instead, the gas returning to the black hole may have been so dense that different parts of the stream began to collide with each other. These violent collisions could have circularized the debris into a stable, long-lived accretion disk much more gradually than in the simple model, essentially creating a slow drip feed for the black hole that could power the X-ray emission for years. Another, more exotic idea involves the incredible magnetic fields that must be generated in the chaotic maelstrom of the forming disk. It is possible that the black hole's powerful gravity and rotation are winding these magnetic fields into a tightly coiled spring of energy. This magnetic structure could then act like a steady governor, regulating the flow of material inward and converting gravitational energy into heat with an efficiency that keeps the inner disk hot and glowing in X-rays far beyond its expected lifespan. Yet another fascinating possibility is that we are not seeing the direct glow of the accretion disk at all, but rather the echo of that light being reprocessed. The initial flare from the disruption would have sent a tremendous pulse of radiation out into the surrounding environment, perhaps illuminating a pre-existing cloud of gas and dust that had been orbiting the black hole unnoticed. This cloud, heated by the initial blast, could then re-radiate the energy slowly over many years, creating the illusion of a persistent central engine. Or the long-lasting X-rays could be coming from a powerful jet of material that was launched at nearly the speed of light from the black hole's poles during the disruption. If this jet is pointed almost directly at us, its steady, high-energy output could dominate the signal for a very long time. Each of these explanations pushes at the boundaries of our understanding, requiring new physics for how matter behaves under the most extreme gravitational stresses imaginable. What makes Assassin 14 lie so invaluable is that it has become a natural laboratory, a unique cosmic experiment allowing us to probe the laws of physics just outside the point of no return. By meticulously monitoring the subtle changes in the X-ray light over years, astronomers can map the geometry of the accretion flow and measure properties like the black hole's spin, a parameter that is incredibly difficult to determine by any other means. The stable nature of the emission provides a clean, continuous signal to analyze, free from the chaotic variability that often plagues the study of active black holes. This single event has fundamentally challenged the classical picture of a tidal disruption as a simple, short-lived flash in the pan. It has revealed these occurrences to be far more nuanced and complex, with the potential to illuminate the dynamics of black hole feeding for years after the initial stellar death. The enduring mystery of Assassin 14 serves as a powerful reminder that even in the most violent and seemingly straightforward cosmic catastrophes, the universe still holds surprises that force us to refine our models of how matter and energy interact in the most extreme environment nature can provide. Having explored the unsettling alignment known as the axis of evil, we return to the cosmic microwave background to confront another of its profound anomalies, a place on the sky that is not just a little different but deeply statistically cold. This is the CMB cold spot, a vast circular patch in the constellation Eridanus where the temperature of the primordial radiation dips far lower than our standard models can comfortably explain. Discovered by the Wilkinson Microwave Anisotropy Probe in the early 2000s and later confirmed with stunning precision by the Planck satellite, this region isn't just a random fluctuation. The sheer size of the cold spot, spanning 1 billion light-years across, combined with the intensity of its chill, makes it a profound statistical outlier. If the universe were indeed the random, isotropic cosmos described by the Standard Model, the odds of such a colossal and cold patch appearing by pure chance are astronomically low, something like 1 in 200. This isn't just a minor imperfection in the cosmic tapestry. It is a gaping hole in our understanding, a place where the universe seems to be whispering that something truly extraordinary happened in its infancy. The most straightforward and least universe-shattering explanation for this cosmic chill is a colossal emptiness. Astronomers call this a supervoid, an immense region of space that is largely devoid of galaxies, galaxy clusters, and even the faint, diffuse gas that makes up the cosmic web. The physics behind how a void could cause a cold spot is rooted in the work of great minds like Einstein and Chequers, through an effect known as the integrated Sachs-Wolf effect. As photons from the CMB travel across the universe for over 13 billion years, they climb in and out of the gravitational potential wells created by large concentrations of mass. Normally, as the universe expands and these gravitational wells become shallower, a photon climbing out loses a bit more energy than it gained falling in, resulting in a net redshift, a very subtle cooling. When a photon passes through a vast, underdense region like a supervoid, the effect is reversed in a way. The photon, in a sense, rolls downhill into the void and then has to climb out the other side. In a static universe, the energy loss and gain would cancel out. But because the void itself is growing deeper and more pronounced as the universe expands, the photon loses a net amount of energy during its journey through this growing emptiness, causing it to appear ever so slightly cooler or redshifted by the time it reaches our telescopes. A sufficiently enormous supervoid could, in theory, produce the significant temperature dip we see in the cold spot. It would be a cosmic mirage, a cold shadow cast by a great nothingness. For years, this became the great race in observational cosmology, to find the supervoid that must be responsible. Teams of astronomers meticulously mapped the distribution of galaxies in the direction of the cold spot, using powerful telescopes to conduct deep field surveys, counting galaxies and measuring their redshifts to construct a three-dimensional map of that entire sector of the universe. The results, however, have been deeply puzzling and frustratingly inconclusive. While some surveys did identify a large underdense region in the general vicinity, a notable absence of galaxies, this proposed supervoid was consistently found to be not nearly as vast or as empty as the cold spot theory demanded. The numbers simply did not add up. The observed void, while large, appeared to be far too shallow to account for the profound coldness of the CMB in that direction. It would be like trying to explain the deep chill of a mountain peak by pointing to a small, grassy hill in the distance. The scale is just completely wrong. This left cosmologists with a difficult choice. Either our understanding of the integrated Sachs-Wolf effect and how photons interact with large-scale structure is fundamentally flawed, or the cold spot has a far more exotic origin. This is where the mystery elevates from a problem of cosmic cartography to a potential window into the multiverse. If a supervoid cannot explain the cold spot, then we must turn to explanations that originate from the very beginning of everything during the period of cosmic inflation. One of the most breathtaking hypotheses is that the cold spot is a cosmic bruise, the imprint of a collision between our universe and another, separate bubble universe in the wider multiverse. In this mind-expanding scenario, what we call the Big Bang was just the inflationary expansion of our own local cosmic bubble. Beyond our observable horizon, an endless froth of other universes, each with potentially different physical laws, could be constantly bubbling into existence. According to this theory, if another such bubble universe had collided with ours during the early stages of inflation, the tremendous energy released in that impact would have left a distinct signature on the CMB of both universes. The collision would have deposited a massive amount of energy into a localized region of our cosmos, which then expanded to a colossal size as inflation continued. This region would appear to us as a vast, cold spot because the collision would have altered the density of particles in that area, subtly changing how the CMB photons were scattered when the universe became transparent. The cold spot in this view is not an emptiness but a scar, the first experimental evidence that our universe is not alone, but is merely one island in an infinite archipelago of realities. Of course, such an extraordinary claim requires the most rigorous scrutiny, and the scientific community remains sharply divided. Skeptics rightly point out that the multiverse explanation, while thrilling, is notoriously difficult to test. It exists in a realm of theory that is, for now, just beyond the reach of direct experimental verification. They argue that we must first exhaust every possible mundane explanation within our own universe before leaping to conclusions that involve an infinite number of others. Perhaps there is a more complex combination of smaller voids and other large-scale structures along the line of sight that, when their individual effects are combined, somehow mimic the signal of a single, giant cold region. Or maybe it is a statistical fluke after all, a 1 in 200 chance that simply manifested in our particular universe, a cosmic roll of the dice that came up odd. The challenge is that we have only one complete universe to observe. We cannot look at 1,000 different SIMB maps to see if cold spots of this magnitude are common or not. For now, the cold spot remains one of cosmology's most tantalizing and persistent puzzles. It stands as a monument to the limits of our current knowledge, a cold and silent question mark on the oldest map we possess, challenging us to determine whether we are staring at the shadow of a great emptiness, the bruise from a collision with another reality, or something even more strange that we have not yet begun to imagine. And now we arrive at the final, breathtaking phenomenon on our list, a concept so dramatic it sounds like science fiction, the existence of runaway supermassive black holes. We are accustomed to thinking of these cosmic monsters as the ultimate anchors, the unmoving hearts of gravity firmly bound to the centers of their galaxies. But Einstein's theory of general relativity contains a stunning prediction that could turn these titans into galactic exiles, violently ejected from their homes to wander the intergalactic void. This is the theoretical phenomenon of the recoiling black hole, and its potential discovery would be one of the most electrifying confirmations of the extreme physics governing our universe. The entire process begins with a collision of titans. When two galaxies merge, the supermassive black holes at their cores are destined to meet. Drawn together by gravity, they begin a slow, spiraling dance, eventually forming a tight binary system. As they whip around each other at a significant fraction of the speed of light, they churn the fabric of space-time itself, emitting immense ripples known as gravitational waves. This emission saps the system of energy, causing the black holes to lose orbital altitude and spiral inward ever faster, until they finally plunge together in a final, cataclysmic merger. This collision is not a gentle coming together. It is a supremely violent event where the two singularities become one. According to the complex mathematics of general relativity, if the two black holes are of different masses, or if their spins are misaligned, the emission of gravitational waves in the final moments will not be perfectly symmetrical. Think of it like firing a rocket engine. If you fire it evenly on all sides, you stay put, but if you fire it more powerfully in one direction, you get a kick. In the final fraction of a second before the merger is complete, the new single black hole can receive an immense kick from this lopsided blast of gravitational wave energy. The velocities predicted by these calculations are staggering, potentially launching the newborn black hole out of its galactic core at speeds of millions of miles per hour, fast enough to escape the gravitational pull of its entire host galaxy. So, how would we ever find such a cosmic fugitive? The hunt relies on searching for a specific, bizarre signature. A supermassive black hole on its own in the dark of intergalactic space would be virtually invisible. But if it was actively feeding just before its violent ejection, it would take its glowing, hot accretion disk along for the ride. This means a runaway black hole would appear as a brilliantly shining quasar, a beacon of intense light completely detached from any visible galaxy. Alternatively, we might catch one in the act of being ejected, where we would see a quasar that is noticeably offset from the precise dynamical center of its host galaxy, or even a bright quasar with a faint, trailing stream of stars stretching out behind it, torn away by the black hole's gravitational pull as it plows through the galactic disk. Astronomers are actively scanning the skies for these very signs, using the most powerful telescopes to measure the positions of quasars with exquisite precision, and looking for any that seem strangely isolated or misaligned. Finding a confirmed runaway would be far more than just adding a new class of object to the celestial zoo. It would be a monumental victory for fundamental physics. It would provide the most direct possible evidence for the existence of gravitational waves from black hole mergers, a key prediction of general relativity operating in its most extreme regime. It would confirm that black holes can indeed have spin, and that these spins can be misaligned, giving us a profound new window into their dynamics. Furthermore, the discovery would help explain a long-standing puzzle: why some smaller galaxies appear to lack a central supermassive black hole altogether. Perhaps they lost theirs in a violent kick long ago. The quest to find these runaway giants is a testament to the predictive power of theory and the relentless curiosity of science, pushing our observational capabilities to their absolute limits in the hope of capturing one of the most dramatic events the universe has to offer: a titan cast out from its throne, forever destined to roam the vast, empty halls between the stars. And so, our journey through 25 of the universe's most profound puzzles comes to a close. We have ventured from the ghostly gravitational pull of dark matter and the repulsive force of dark energy to the fleeting brilliance of fast radio bursts and the static cry of the wow signal. We have encountered stars that dim in impossible ways, interstellar visitors with bizarre properties, and colossal structures in space that defy our most basic assumptions about cosmic order. We have stared into the heart of black holes and grappled with the paradox of lost information, and we have peeled back the layers of the cosmic microwave background to find alignments and cold spots that whisper of a reality far stranger than our textbooks describe. Each of these phenomena, from the galactic to the subatomic, stands as a testament not to what we know, but to the vast, thrilling expanse of what we have yet to understand. Remember, these enigmas are not signs of science failing. Quite the opposite, they are beacons illuminating the very frontiers of human curiosity. Every unexplained signal, every anomalous measurement, every theoretical contradiction is a call to action. It is the gravitational anomaly that pushes us to build more sensitive detectors, the strange stellar behavior that inspires new space telescopes, and the mathematical paradox that forces a complete rewrite of our fundamental theories. The history of science is written in these moments of beautiful confusion, where the universe presents a riddle that, in the solving, expands our minds and our capabilities. The drive to answer these questions is what propels our technology forward and deepens our connection to the cosmos, transforming us from passive observers into active participants in a grand, ongoing discovery. As we stand here on our small, pale blue dot, looking out at this sea of mysteries, it is a moment for profound reflection. We are living in an era of unparalleled cosmic revelation, where every week brings new data that challenges the old and hints at the new. This journey reminds us that the universe is not obligated to conform to our intuition or our current models. It is wilder, more imaginative, and infinitely more wonderful than we can possibly conceive. We are part of a story that is still being written, a narrative of exploration that stretches from the quantum foam at our feet to the great cosmic voids above. Our greatest achievement may not be in finding all the answers, but in having the courage to keep asking the questions, to remain forever humbled and awestruck by the magnificent, mysterious cosmos we are privileged to call home. We would love to hear which of these cosmic head-scratchers captured your imagination the most. Was it the perfect geometry of Hoag's object, the ghostly presence of dark matter, or the terrifying possibility of a runaway black hole? Let us know in the comments below which phenomenon left you the most baffled. If you enjoyed this deep dive into the unknown, please subscribe and hit the notification bell, because we have many more journeys into the secrets of the cosmos waiting for you. The universe is strange, and we are just getting started.